Good morning, everyone. Today we had with us Dr. R. Arun Kumar sir. He is presently working as a assistant professor. Just a minute, sir. Yes, Dr. Arun Kumar sir is presently working as an assistant professor in Department of Civil Engineering at NIT Calicut. He did his PhD from IIT Bombay. He also worked as a post-doctoral fellow at Western University, London, for 2 years. He has published more than 60 papers in journals and 20 papers in national and international conferences. He is a member of various professional organizations like Institute of Engineer, Indian Society for Hydraulics, Water Resources Society. Many awards are also on his credit. He is the recipient of Dr. Jayasekar Endowment Award by Anna University. He was also awarded by Union Ministry of Water Resources Department of Irrigation for his one-off publication in the Journal of Institute of Engineers. He is also recipient of Dr. UC Kothari Best PhD Thesis Award from Indian Society for Hydraulics, Pune, and Award for Excellence in Thesis Work from IIT Mumbai. Thank you, sir. Thank you very much for being with us.
Yeah, thank you very much.
Thank you, madam. Thank you, madam, for the nice introduction.
Yeah, I welcome Dr. Arun Kumar. We have a very good association, and he visited our institute long back for a conference. And he's mainly he worked in optimization area, and lot of good publications and even awards as well. It is to his credit. And the first day, the Professor V. Jyoti Prakash, he has inaugurated our FDP. So he is Jyoti Prakash sir's student, and a nice water resources expert and optimization expert. So I welcome you, sir, and please start the session.
Thank you, sir. Thank you to all. Actually, for better internet connectivity, I am just switching off my video. Somehow
Okay.
I am managing here that internet connection. So
Okay.
I'm just switching off my video. Is my presentation visible?
Yeah. Presentation is visible and you are audible also.
Okay, thank you, sir. Today I'm going to present about linear programming. So as you know, nonlinear programming is the optimization technique. We have several optimization technique. Briefly, I will give an overview about optimization techniques and how to formulate the optimization problem. And then, as I mentioned, the classification of different optimization techniques, and more specifically about some of the nonlinear programming techniques. In fact, quite a lot of nonlinear programming techniques are available, but I will restrict myself to few techniques in that. And finally, I will be discussing about a case study that is optimization of hydropower production from Koyna hydroelectric project that is in Maharashtra. So this is how I have arranged my presentation. And if we have enough time at the end of my presentation, I will also introduce about simulation and the system dynamics simulation. In fact, a part in the model, in this case study, Koyana hydroelectric project, we have developed a simulation model. So that's what that presentation is about. So first, let's start with the general optimization. So we know, so optimization is nothing but it is the procedure of selecting the set of decision variables that maximizes or minimizes the objective function subject to various constraints. So in fact, in our childhood or our school days, we might have heard this problem. Our friends or teachers might have saying this one. So if we have, there are a few children, let's say 4 or 5 children are there, and we have some 5 chocolates, and how to distribute the chocolates. Okay, so that's the problem. So how to optimally or in a best way how we can distribute that. So here there are no constraints. Simply on the one end, if you have 5 children, on the other end, if you have 5 chocolates, easily we can distribute 1 chocolate to each student. Okay, so technically we can formulate a mathematical problem for this. So here, by distributing what we are going to achieve, actually the students may become happy. So here our objective function is to maximize the happiness among these students. So when there is no constraint, easily we can distribute 1 chocolate to all the students, or otherwise depends upon the happiness index. We can develop an index for happiness, and we can distribute some chocolates to few students and no chocolate to any student. So this is without any constraint. If you put a constraint, let's say each student should get at least 1 chocolate, then everyone will get 1 chocolate. So that problem is nothing but the optimization problem. So it's nothing but it is the procedure of selecting the set of decision variables that maximizes or minimizes the objective function subjected to the system constraints. So here the objective function is nothing but we are maximizing the happiness among the students. So that is our objective function. And what is that constraint? At least one, each student should get at least 1 chocolate. So that is called constraint. Similarly, if you take any field problems, we may have this kind of experiences. Obviously, all the real life problems or all the field problems will have plenty of constraints. And on the other hand, it may also have a lot of decision variables. Even if you are designing a parking lot, so how to design in a proper way such that we can park maximum number of cars in that. So what's the dimension? So here the constraints are the dimension of the plot and the dimension of the cars and the entry and the exits. So these are different ways are there. So for each and everything, we have to formulate some mathematical model. We have to write some equations, mathematical equations describing each and everything. Then we have to try to solve that using various optimization techniques. So based on the type of the problem, whether it is a linear one or the non-linear one, like that, whether discrete one or continuous one, concave, convex, like that. Based on that, we have to choose appropriate optimization technique, and then we have to apply that. Finally, we have to arrive at a best feasible solution. That the best feasible solution is called the optimal solution. And again, when we are discussing about the best solution or the optimal solution, there also exist many solutions. One is global optimal solution, and another one is the local optimal solution. So when we are discussing or when we are developing any optimization model, first we have to understand all those basic concepts. I hope you might have now come across all those things in the last 4 days. So I am just skipping all those topics. And moreover, in this presentation, throughout my presentation, mostly I will be giving some examples from water resources. Since my specialization is in water resources, I will be just giving most of the examples from that domain. Anyway, I will try to be more general, and I will try to give as many as examples from other domains as well. So yeah, as I mentioned, there are numerous optimization techniques are there. Actually, we can classify or we can categorize these techniques, optimization techniques, broadly into 2 specific categories. One is conventional techniques, and another one is the evolutionary algorithms, or otherwise the artificial intelligence based soft computing techniques. These conventional techniques include the linear programming, non-linear programming, goal programming, mixed integer programming, like that, dynamic programming, like that. There are many such techniques are there. And then we have the recently evolved, developed techniques known as evolutionary algorithm. These evolutionary algorithms mimic the process in the nature. For example, if you take the genetic algorithm, it's nothing but it's based on the principles of Darwin's survival of the fittest. It basically mimic the our human process, like this mutation, crossover, and the mutation, how we evolve over different generations. That procedure is called genetic algorithm. Similarly, we have particle swarm optimization and colony optimization, differential evolution algorithm, like that. There are nowadays in every issue, if you take a scientific journal which is related to optimization or which is related to hydroinformatics, you can see in every issue there is one new optimization technique is introduced. So every day we are developing new and new techniques like that. But if you look at the problem, the nature of the problem, we don't need this many techniques. Mostly, if you look at all the techniques, the performance of all the techniques are quite similar. But however, sometimes they may differ from other techniques or each other based on the working principles, how they search the optimal solution. That's the first difference. And second one will be how quickly they attain the global optimal solution. So these two predominantly plays a major role in selecting a appropriate technique. In fact, I have a slide with respect to water resources engineering about various optimization techniques or about various optimization models. In fact, I will discuss that later. Okay, so first let us start with the conventional linear programming technique. So I am just mentioning all these techniques like linear programming, non-linear programming, goal programming, or dynamic programming as conventional techniques, because these are all very age-old techniques, and there is a major difference between these conventional techniques and the recently evolved evolutionary algorithms. The major difference between these techniques is these conventional techniques will arrive at the optimal solution based on some iterative procedure. So from one step to next step, we have to find out the derivatives. It will use the derivatives to find out the optimal solution. So that is, we have to, that derivatives is nothing but basically we are finding out the slope, the gradient. So that will take us to the optimal solution. It's a kind of iterative process. Whereas if you take the evolutionary algorithms or the swarm intelligence techniques, most of those techniques are population-based search techniques. So we have a group of population. So among that group of population, it will search the best optimal solution. So that is another major difference between the conventional techniques and the evolutionary algorithms. So if you take this linear programming, so this linear programming technique can be applied to the problems that are linear in terms of objective functions and constraints. So if your objectives are very simple and straightforward, and if it is linear in nature, then we can simply apply the linear programming techniques. So it is one of the very widely used optimization techniques, and we are using that for very long back. So over a period of time, many modifications and improvements have been done to this linear programming technique to use in the real world applications. And sometimes the nonlinear problem will also be converted into a linear problem, like a piecewise linear problem. The entire nonlinear problem will be broken down into smaller subproblems, piecewise linear problem, and then each problem will be solved separately. These examples include the different schemes for the linearization of nonlinear relationships and constraints, and the use of successive approximations. And then we have the nonlinear programming. So nonlinear programming is an optimization approach used to solve problems when the objective functions and the constraints are nonlinear in nature. So when the objective functions and constraints are not in linear form, or if it is in a nonlinear form, then we have to basically go for the nonlinear techniques. So most of the real world problems are nonlinear in nature. And here this is a successful application of nonlinear programmings are quite available for nonlinear problems such as unconstrained and linearly constrained problems, quadratic problems, convex problems, and non-convex problems, and geometric problems. Several studies have been reported. We have well-established literature for this application of linear and nonlinear programming. So apart from linear and nonlinear programming, there is one more technique in conventional optimization methods, that is dynamic programming. So this linear and nonlinear programming have limitations as well. To overcome that limitation, the other conventional technique which is developed in dynamic programming. The major limitation in the nonlinear programming is that the method is generally unable to distinguish between a local optimal solution and a optimal solution. So this dynamic programming was developed by Bellman. So this dynamic programming offers advantages over other optimization tools since the shape of the objective function and the constraints do not affect it, and as such, it has been frequently used in many water resources systems management. Actually, if you look at this dynamic programming, we have to discretize the problems into several set of stages and states. So at every stage, a number of possible conditions of the system are identified. And the solution is identified at each individual stage, given that the optimal solution for the next stage is available. So as it is here, this dynamic programming will discretize the problem into stages. And again, for each stage, we can have different system states. So it will start stage by stage process, and finally it will arrive at the optimal solution. And in the recent past, most researchers have been looking at approaches that combine the efficiency and an ability to find the global optimal solutions. And one group of techniques known as the evolutionary algorithms seems to have a since the promise of achieving both. So as I mentioned earlier, even though we have numerous conventional techniques optimization of problems for solving the optimization problems, but still many people are interested looking forward for a new technique, and there involves the evolutionary algorithms. So I discussed about the dynamic programming. One of the major limitation or the problem in the dynamic programming is curse of dimensionality. So the problem, the thing in dynamic programming is, since we discretize the problem into several stages and states, if we have more number of stages and states, usually the dynamic programming results in curse of dimensionality. So that is one of the major limitation in the dynamic programming. Otherwise, dynamic programming of the nonlinear programming, which is also one of the technique which can be to solve many nonlinear problems. Okay, so to overcome that, now algorithms have been developed. So as I mentioned earlier, here I have categorized various models based on their objectives, their purpose. This categorization is more specific to the reservoir operation in water resources. So if you take any dam or reservoir, actually it serves many purposes. Like we can supply the water for irrigation, we can generate hydropower production from the reservoirs, and then we can use it for a recreational purpose, for flood control purpose, for domestic and industrial water supply, like that. As we know that the reservoir serves many purposes. Basically, based on its purposes, we can categorize these things. So based on the number of reservoirs, we can categorize the optimization problem, that is the reservoir optimization problem, into a single reservoir problem or a multi-reservoir problem. and based on the purpose it serves, whether it is specifically designed for serving a single purpose, then we can say it is a single purpose reservoir. But at the same time, if it serves multiple purposes, like for supplying water for irrigation, hydropower generation, and flood control, then that will come under the multi-purpose reservoir. And based on the number of objectives, we can categorize the optimization problem into single objective problem and multi-objective problem. And based on the type of objective function, whether it is minimization type or maximization type, again that can be categorized into two categories. And based on the objectives, whether it's supplying for a municipal and industrial water supply, or for irrigation, hydropower generation, flood control, ecology, and aquaculture. So once you formulate your mathematical problem, then we have to choose appropriate technique to solve that mathematical problem. So here we have both conventional and soft computing techniques. So in conventional techniques, so we have linear programming, nonlinear programming, dynamic programming, goal programming, and in fact there are many other techniques. In fact, if you take linear programming, then linear programming itself is it's a lot of methods. Tools are available. Similarly, in nonlinear programming, and on the other side, in soft computing techniques, we have genetic algorithm, differential evolution algorithm, and colony optimization, particle swarm optimization, and many others. Another major issue in water resources is these water resource problems are inherently stochastic in nature. That is, it has some random process inherently present in this. So we have to consider that randomness present in the water resource variables. Especially if you take the rainfall, we cannot say that there will be 100% surety there will be rainfall tomorrow or in the coming days. There will be always some kind of uncertainty associated with that. So we have to always address that uncertainty when we are developing any model. So address that, we have to develop our model as a stochastic model. Okay, so in conventional techniques, that is considered as stochastic, or if you are not considering that uncertainty, then our model will be a simple deterministic model. Sometimes that stochastic, that uncertain nature is also considered as chance constraint. And other than that, we are also having fuzzy technique. But if you look at the soft computing techniques, the recent soft computing techniques, most of the soft computing techniques are random in their process, in their working principle itself. If you take genetic algorithm, it's having several steps like selection, crossover, mutation, like that. So in each and every process, in that each and every step, it has some inherent randomness in the process itself. So mostly in these soft computing techniques, these uncertainty in the water source variables are not explicitly considered in that. So that randomness is already accounted in the model process. Whereas if you are using any conventional technique, then we have to explicitly consider that randomness present in the variables. So this classification of these optimization models is more specifically for the reservoir operation. So our problem complexity increases on the right side. Suppose if our system of reservoir is a multi-reservoir system, if you take any basin, in the particular basin there will be plenty of reservoirs starting from the upstream of the basin to the downstream of the basin. And nowadays most of the reservoirs are not standalone reservoirs. They are connected with the other reservoirs. Water is being transferred from one reservoir to the other reservoir. Moreover, we are also discussing about interlinking of rivers and so. So each reservoir in the system in a basin is on one way or other way it is connected. And on the other hand, most of the reservoirs are multi-purpose reservoirs. Even though some of the reservoirs were constructed for a specific purpose at the time of construction, maybe in the 1960s, most of the reservoirs in India, the biggest large reservoirs in India were constructed during the first and second 5-year plans, that is during 1960s, during that time. So even though some of the reservoirs are specifically constructed for a particular usage, but over a period of time, with the increasing in demand from many other sectors, all those reservoirs were converted into multi-purpose reservoirs. And one of the classic example for this one is the Hirakud reservoir in Orissa. when it was constructed, the major purpose of that reservoir was to control the floods. Okay, but over a period of time, that has been converted into a multi-purpose reservoir. Now it has the objective of satisfying the irrigation demands. Hydropower production is there in addition to the flood control. And then how many objectives we are considering? We are simply obviously when there are multiple purposes are there, when a reservoir serves various purposes, then it is always efficient or effective to consider it as a multi-objective problem. Then only we can solve or we can satisfy all the objectives at the same time. So if you look at on the right side, this multi-reservoir, multi-purpose, multi-objective, when you consider all those things, the complexity of the problem increases manifold. So in that case, we have to choose an appropriate technique to solve our problem. Okay, so let's see how to formulate the optimization models. So here it is. In fact, I specifically wrote this sentence: model formulation is the most difficult part. So the why I have written this sentence in the sense, ultimately we have to write or we have to express everything in terms of mathematical equations. So actually those mathematical equations should replicate the real life process. If it is not replicating that real life process, then our equations, our mathematical model are not the exact same as the real life model. Okay, so we have to actually replicate what it is actually happening in the field. So bringing all those concepts, all those constraints in the form of equation is a really challenging task. So we have to be extra careful in developing our mathematical model. That is in formulating the optimization model. So how to formulate that optimization model? Is there any criteria or any guidelines is there? And Wagner in 1975, he has offered some guidelines for the formulation of mathematical optimization models. So these are the guidelines proposed by the Wagner, they are 1975. The first point is what are the key decisions to be made and what problem is being solved. So we have to first understand our problem and what is our main decision here, what we are trying to achieve here by solving this problem, that we have to understand first. And what makes the real decision environment so complex as to require the use of an optimization model. What elements of complexity are incorporated in model and what elements are ignored. So if you take let us take the dam problem, reservoir problem. So if you take the dam problem, it have lot of constraints. Let's say if it is a irrigation reservoir, then first we have to determine what is the irrigation demand, how much water we have to supply for the demand. Again, we have to look out the canal carrying capacity also. If the canal carrying capacity is less than the demand, then we obviously we cannot supply all the demand. So and look some other aspect, if it is a flood control, if it is combination of irrigation and flood control, then how to maintain that that one. So here sometimes we may need to make some compromise between the constraints, which one should be given priority or which element is having more complex that has to be incorporated into the model, which one can be relaxed or which one can be ignored. Depends on the problem and the significance of the problem that we have to decide. And what distinguishes a practical decision from an unusable one in the environment? Again, that's based on the systems. What distinguishes a good decision from a poor one? As a decision maker, how would the results of the analysis and what is your interpretation of results? In what ways might you want or need to temper the results because of factors considered in the model? So these are some of the key guidelines proposed by WAG 75 for developing the optimization model. So we have to on these guidelines to develop an optimization model that actually replicates the condition. So if our optimization model, if our mathematical model actually replicating the field conditions, we cannot implement the whatever we are obtained from the model. So our model results should be a practically implementable one. So that we have to keep it while doing the optimization model. And then algebraic representation of the optimization model, or the mathematical representation of the optimization model. So in most of the problems, the aim of the optimization model is to either maximize or minimize some objective functions and subjected to some constraints. So basically our model objective function will be either maximize or minimize some objective functions. If our model doesn't have any constraint, then our model will be a simple optimization model. But in reality, even if you take any problem or any simple problem, it will have plenty of constraints. So one of the example what I showed is the designing a car parking lot. So there we have to first look at the dimensions of the plot available, and then in fact we have to look at the entrance and exit, and we have to look at the orientation, and then we have to look at the dimensions of the car, and accordingly we have to prepare the parking lots. So there also, only if you consider all those constraints, if you bring all those constraints into your model, then only it will replicate your model results, whatever we are obtaining from the optimization model, that can be easily implementable in the field. But otherwise, if we are not considering all those constraints, whatever we are obtaining from the optimization model, the results, that cannot be implemented. Even that if that is implemented, then that result or that will not work. So the first step in the formulation of the optimization model is the framing the objective function. So our objective function will be either minimization type or maximization type. So when we discuss about the objective function, then we have to look at the decision variables. What all the parameters we are going to decide or we are going to solve for. So such parameters, such variables are called decision variables. So the first step is to decide which are the decision variables. So these are the quantities that can be varied and so affect the value of the objective function. The second step in the formulation is to express the objective functions in terms of decision variables. We must write down the constraints that restricts the choice of decision variables. And one common sense constraint is that many variables cannot realistically be negative. This is one of the most important point in optimization model. Even if we develop any optimization model, any mathematical model, then finally we will write one constraint known as non-negativity. That is, none of the decision parameters or the decision variables are negative parameters. They are always greater than 0. So so first we have to understand the problem. So based on that, we are developing the objective function. We are determining the decision variables, and based on that, we are developing the objective function, whether it is maximization or minimization. Then we are bringing in all the constraints into the problem in the form of mathematical functions, and then we are putting the non-negativity constraint. So this framework is a complete representation of any mathematical problem. And then here is a simple example. If let x of j be the level of activity j for j equal to 1 to 2 dot n, we want to select a value for x of j. So our objective function be c1 into x1 plus c2 into x2 plus dot cn to xn. Here x1, x2, xn are nothing but the decision variables, and c1, c2, cn are nothing but cost functions. So either we are maximizing or minimizing this objective function. That represents the type of the objective function. And then it is subjected to certain constraints. So let's say a1 x1 a2 x2 plus dot 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 an xn less than or equal to a. So this type of constraint, this first constraint is nothing but inequality constraint. The first one and the last one is the inequality constraint. The middle one is the equality constraint. So this use a classical optimization problem where you have a specific objective function which is subjected to various constraints. Once you formulated this objective function, then we have to solve the objective function. There we have to choose appropriate technique to solve the functions. Even before choosing that appropriate technique, there are some steps are available, so that we shall discuss now. So for any optimization model, so what are all the possible answers? So sometimes there will not be any feasible solution, that is no feasible solution. For any problem, especially the optimization problem, we will have the solution space. If the solution is not within that solution space after implementing the constraint, then it is infeasible problem. There may be no values for x of j. That is our decision variable. We cannot find any appropriate optimal value for the decision parameter for this decision variable. So in that case, our constraints are not satisfied. So such a problems are called infeasible problem or infeasible solution. And second one, sometimes it may have a unique optimal feasible solution. If you have only one single optimal solution, that single optimal solution will be is also called as global optimal solution. And then we will have a solution space. In that, whatever solution it is there, such solutions will satisfy all the constraints. When your solution satisfy all the constraints, then such a solution is called the optimal solution, because it is satisfies all the constraints. But the thing is, it may not be a global optimal solution. Sometimes it may be a local optimal solution. Locally within that small space, it may be the best solution. It will satisfy all the constraints. But if you look at the entire such a space or the solution space, it may not be a global optimal solution. So in that case, we will have multiple local optimal solutions. That is more than one optimal feasible solution. And then a feasible solution such that the objective function is unbounded. So there is no boundary at one end. It will be infinite. That is, the value of the function can be made as large as desired in a maximization problem, or as small in a minimization problem by selecting an appropriate feasible solution. So for any optimal optimization problem, we may encounter any one of these answers. So what are the steps if you are manually solving any optimization problem? If any optimization problem is having lesser number of decision variables, then we can easily solve all those optimization problems manually by choosing an appropriate technique. So in that case, we have to follow some standard procedures. So what are the standard procedures? First, changing the sense of optimization. That is, sometimes we may need to convert the maximization problem into a minimization problem, or minimization problem into a maximization problem. So this usually we can do by multiplying the objective function by -1. So by doing so, we are actually changing the nature of the optimization problem. We are converting a maximization problem into a minimization problem, or a minimization problem into a maximization problem. And second one is the changing the sense of inequality. So we have seen one of the constraint as the inequality constraint. That is, it is not equal. It's either less than or equal to type, or greater than or equal to type. So those inequality constraints can be converted into equality constraints. So for that, we have to either add slack or surplus variables. So by adding slack or surplus variable, we can convert the nature of the constraints from inequality to equality constraints. And then in the same way, we can also convert the inequality constraints to equality constraints. That is by multiplying with some ratios. And finally, we are adding all those ratios to equal to 1. So like that, we can convert the equality constraint into an inequality constraint. So by following these procedures, we can change the type of the problem. For example, if your problem was earlier a maximization type, then we can convert that into minimization type, and we can actually, this process is nothing but it's a simplification process. Sometimes we cannot solve the problem as such. So in that case, we have to modify the problem in a more simplest way so that we can easily solve that problem. So for that, we have to adapt all these procedures. Once we do all these things, then our problem become a simpler one. Then we can choose an appropriate technique, and then we can solve our problem. So these are the basics in developing optimization model. First, we have to look at our problem, what our exact problem is, and then for that problem, we have to develop the optimization model, which is having a particular a specific objective function. And for that objective, for developing that objective function, first we have to decide the decision variables, what we are trying to optimize. And then we have to bring in all the constraints. Then once we have that optimization problem, that we have to look whether that requires any change or we need to convert the problem. So once it is done, we have to choose the optimization technique. So as we have discussed earlier, there are many optimization techniques are there, starting from simple linear programming to recently developed evolutionary algorithms. So here in this lecture, I will be briefly discussing about the nonlinear programming. In fact, if you take the nonlinear programming, there are plenty of methods are there. In fact, nonlinear programming for a simple unimodal problem, and there are separate techniques for unconstrained problems, and there are separate techniques for constrained problems. So here in this lecture, I will be restricting myself to only very few techniques. So nonlinear programming for one-dimensional minimization methods or one-dimensional unimodal mathematical problems. So for that, we are having two methods. One is elimination method. So under elimination method, we have unrestricted search, exhaustive search, dichotomous search, interval halving method, Fibonacci method, golden search method, and then the second method is interpolation method. There we have quadratic interpolation method, cubic interpolation method, direct root method, and under direct root method, we are having Newton method, quasi-Newton method, and finally secant method. And the nonlinear programming for constrained and unconstrained problems. For unconstrained optimization techniques, we have direct search methods and indirect search methods. Under direct search methods, we have random search method, grid search method, univariate method, pattern direction method, simplex method, and in indirect method, steepest descent method, conjugate gradient method, Newton's method. Nonlinear programming for constrained optimization includes again direct methods and indirect method. In direct method, we have random search methods, complex method, sequential linear programming method, hill climbing method, and in indirect method, we have penalty function method and the Lagrange multiplier method. So here let us see how to solve a nonlinear optimization model and its solution procedure. So since we are discussing about the nonlinear technique, as I told, this nonlinear technique will arrive at the optimal solution based on some iterative procedure. That is, from one step to next step, it progresses through some iterations. It may find the derivatives or the gradient or the slope. So by doing that iteration, we are trying to arrive at the optimal solution. Whereas this evolutionary algorithms that will usually search the optimal solution from a solution space, that is from a population of solutions. Okay, so here in since these conventional methods are based on iterative procedure, we have to basically find out the derivatives in each and every step. So here let us consider a case. So let us consider this example. We have a river. So from that river we have to distribute the water to 3 industries, that is 3 firms that belongs to the same corporation. So here we have to decide how much quantity of water that has to be delivered to these 3 firms such that we can obtain the maximum benefits from these 3 firms. Let us say there is a Q quantity of discharge is flowing in the river, and we have 3 firms. Okay, so for these 3 firms we have to optimally allocate the water such that we have to obtain the maximum benefit from the 3 firms. So the 3 firms here, it is denoted by the index J. So J equal to 1, 2 and 3. So 1, 2 and 3 represents the firms, and here the decision variable is how much water we are allocating to each firm. So that is our decision variable. So that decision variable here is represented by X. So X of J. So that is our decision variable. So if you substitute J equal to 1, that is X of 1, X1. So that represents the quantity of water that has to be up to the firm 1, and X of 2, that is X2. So that is the quantity of water we have to distribute to the firm 2. So like that. So the problem is to determine the allocation of Xj of water to each of 3 firms that maximize the total net benefits obtained from all 3 firms. So here our optimization problem is a maximization type problem. We have to basically maximize the benefits obtained from all these 3 firms. So for that we have to form the objective functions. The total amount of water available is constrained or limited to the quantity Q. So the constraint is here, it is the total amount of water availability, that is the constraint here, that is mentioned as Q. So let us take the net benefits which is obtained from each firm as it is mentioned here. So the net benefit obtained from firm 1 is 6x minus x1 square. This is just an example. And then for net benefit from firm 2, that's equal to 7x2 minus 1.5 x2 square. And from the third firm, it is 8x3 minus 0.5 x3 square. And the figure shows here the water allocation versus the net benefit. So each of these problem forms a concave curve, and as the allocation increases, you can see that in the x-axis it shows the allocation x1, x2 and x3, and on y-axis we are having the benefits, net benefits from firm 1, firm 2 and firm 3. So after a certain limit, after a certain point in all the 3 firms, if the allocation increases, actually the net benefit decreases. Okay, so from this we can have 2 conclusions. One is these are all these 3 functions. These functions are concave functions exhibiting a decreasing marginal net benefits with increasing allocations, and these functions looks like a hills. So this we can solve by many methods, and one of the commonly used approach is the calculus approach. So in calculus approach, we have to just take the derivative of each function. So calculus can be used to find the allocation to each firm that maximizes its own net benefit simply by finding where the slope or derivative of net benefit function for them firm is equal to 0. So that is just to take the derivative of this objective function with respect to that allocation, then we have to equate that to 0. So that point will give you the optimal solution. So like that, for each firm we have to find out the derivative with respect to its allocation, and then we have to equate it to 0. So if you take the first frame, take the derivative with respect to x1, so that is 6 minus 2x1. And then if you equate that to 0, then you can find out what is x1. So here x1 will be equal to 3, right? So when x1 is equal to 3, then we can obtain maximum benefit from this firm 1. So that's the solution based on the calculus approach. So that is the derivative dnb x1 divided by dx1 of net benefit function of for firm 1 is 6 minus 2x1, and hence the best allocation to firm 1 would be 3. Similarly, we can obtain the best optimal solutions for firm 2 and firm 3, and those two answers are 2.33 and 8 respectively. So the total amount of water desired by all firms is the sum of each individual firm, and that works out to be 13.33. So here we are having 3 and 2.3 and 8. So summation of this is equal to 13.33. So here we have not considered the total quantity of discharge. That is, in our previous problem, last line it is mentioned as the total amount of water available is limited to a quantity Q. So far we have not considered the quantity Q. If that is we have not taken into that constraint into our problem. In that case, if there are constraints associated, follow the calculus approach and the solution. But if you put that constraint, let's say that Q is only 6, the total quantity of water available is only 6 units, then not allocate this much quantity of water to these individual firms, because here if you allocate this much quantity, then the total requirement will be 13.33 flow units. So here we have lesser quantity of water available, so we have to go for a different one. However, only 6 units of flow are available for all 3 firms. So constraint renders the previous solution infeasible. So in this case, we want to find the allocations that maximize the total net benefit obtained from all firms, subject to having only 6 flow units to allocate. So in this case, the simple calculus method will not be suitable technique. So we have to look for a different technique. So let us work out this using a method known as hill climbing method. So one approach to find the particular allocation that maximizes the total net benefit derived from all the firms in this example is an incremental steepest hill climbing method. So this method, that is the hill climbing method, divides the total available flow Q into increments and allocates each additional increment so as to get the maximum additional net benefit from that incremental amount of water. This procedure works in this example because the functions are concave. That is, the marginal net benefit decreases with increase in the allocation. So this is the schematic sketch or the algorithm of hill climbing method. In hill climbing method, we have to set the initial conditions, that's decision variables as 0. That is x1, x2 and x3 equal to 0. And we have to decide the incremental. Actually, this method divides the available flow Q into increments and allocates each increment so as to get the additional benefit. So here we have to determine this delta Q. Again, that depends on us how much increment we are giving. So and then we have to add that increment with the available quantity. Initially, our available quantity is 0. We are starting the problem with the 0 with the initial step, and then the next step we are adding that increment with the availability. If that increment is less than the river flow, that's the total river flow, then we have to go to the previous step. That is, there is no allocation. We have not done any allocation to the individual firm. Again, we have to go and add the increment until the Q is greater than the river flow. Q is less than the river flow. If the Q is greater than the river flow, then we have to proceed for the next step. So we have to check whether Q is greater than Q max. If it is greater than Q max, then we have to stop the iteration. If it is less than Q max, then we have to make allocation to the individual frames. Whichever frame is giving maximum net benefit, for that frame we have to allocate the that incremental water. Okay, so this actually we can see by an example. So it's same problem. So these are our objective functions for each three frames. So we are having a river flow, and from that river we have to allocate water to three different firms. Okay, so these are the objective functions for the three firms. 6x1 minus x1 square. For the next second firm, the objective function is 7x2 minus 1.5 x2 square, and third firm, so that is 8x3 minus 0.5 x3 square. Okay, so according to this hill climbing method, in the first step, let us take the maximum quantity as 8. Again, it's also given in the problem. So in the initial step, Qi equal to 0, and here let us consider the incremental allocation, that is delta Q as 1. Okay, so here our iterations are there. This first column represents the iteration number, and here it's a Qi, that's a quantity of flow in each iteration, and this is the river flow. And x1, x2, x3 are nothing but the allocation to all three individual terms, and these are the objective functions. This is the objective function for the first frame, that is 6 minus 2x1. So derivative of this objective function, 7 minus 3x2, 8 minus x cube. Okay, so in the first step, our Q equal to 0 and delta Q equal to 1. Okay, so the river flow is actually 2 units, right? So we can't satisfy this condition. For the first step, Q equal to 0, whereas R equal to 2. So our condition, this is not satisfied. So we have to go to the previous allocation, and then we have to add the increment with the Q. So our increment is 1 here. So 0 plus 1, 1. Now Q, the second iteration Q has become 1. Again, we have to compare the Q with R, that is the R is nothing but the river flow. Here R is 2. Again, Q is less than R. So in the second iteration also, Q is less than R. So again, we have to go back to the previous step and add the increment. So in the third iteration only, if you add the again increment, 2 plus 1, 3. So in the third iteration only, our Q is more than or greater than R. That is Q is 3 and R is 2. Right. So that's why in this it has given 1, 2, 3. So for 1, 2, 3, there is no allocation of units. So that's why they have combined the first 3 steps here. Okay. So in third iteration only, Q is greater than R. So we are directly coming to the third step, and then here the river flow is 2. Okay, and then still we have not made any allocation. Okay, only our discharge Q is greater than R. So our allocation is 0 only. So if you substitute 0 here, so if you substitute the 0 in the derivatives of the objective function, then we will get the benefits. So from the frame 1, we are getting 6 units of maximum benefits, and from frame 2, we are getting 7 units of maximum benefits, and from frame 3, we are getting again 8 units of maximum benefit. So here Q plus delta Q is 3, and our river flow is 2. So we have to allocate the water to the frame whichever is giving the maximum benefit. So among these 3 frames, frame 1, FIM 2 and FIM 3, when you compare all these three firms, third FIM, that is third company, that is giving the maximum benefits of 8 units. So we have to allocate that delta Q to third unit. So we are allocating that delta Q to the third unit. So X3 is allocated 1 unit of water. Now the net benefit is, so here we have to substitute the X3 here. So if you substitute X3 here, so 8 minus 0.5, that is 7.5. Now we have to add the increment. Now fourth step, our Q will become 3 and river flow is 2. So first two FIMs doesn't have any allocation, and third FIM is having 1 unit allocation. And substituting these values and the derivatives of net benefits, we are getting this as the answer. That is, first unit is having 6 unit as maximum benefit, and second FIM is having 7 unit as maximum benefit, and third unit is having 7 units of maximum benefit. So Q plus delta Q here is 4. And therefore is 2. So again, here we have to look which firm, which company is giving maximum benefit by allocating these units. Again, if you look at, if you substitute the values here and if you work out this one, third firm will be giving maximum benefit. Okay, so we have to allocate the delta Q quantity of water to the third firm. So like that, we have to continue this process until we reach the termination criteria. So what is our termination criteria? Again, this one. Q is, if Q is greater than Q max, then we can stop the iteration. That is, our Q max problem is 8, maximum 8. So when Q reaches the maximum quantity, then we can stop the iteration. So at the final step, all the three firms, that is company 1, firm 1, firm 2, firm 3, that has resulted maximum of 4 units as net benefits. Okay. Sir, if you look at actually these optimization problems, if you take any optimization technique, actually that most of the techniques depends on the discretization of the variables. What is the incremental parameter we are considering? In fact, that's what I told, that this dynamic programming, that's a very good optimization conventional optimization technique, which can be used for both linear type as well as non-linear type of problems. Okay, so there in dynamic programming, we have to discretize that the problem into several stages and the states. So when the discretization is very fine, that means you will get a very good best optimal solution. However, with finer discretization, the problem may results in curse of dimensionality. So here also we consider, we have assumed that delta Q, initially we took delta Q as 1. That's somewhat a higher discretization, higher interval. If you reduce that delta Q, then our solution will become more finer. So if you take in this problem here, this problem is solved using very fine delta Q, that is delta Q is almost close to 0. So here we have different units of allocation, unlike previous problem. So here in previous problem, when we have higher interval, almost all resulted in similar maximum marginal benefits. But, allocation is very fine, then we have a different type of allocation here. The allocation for x1 is 1 unit, x2 is 1 unit, and x3 is 4 units. Whereas when the delta Q is very fine, then the entire allocation changes. X1 is 3 units, x2 is 2.33 units, and x3 is 8 units. And the total net benefit here works out to be 49.2 units, whereas in the previous problem, it's almost 35.4 only. So with the increase, with the size of the increment, or sometimes it's based on the discretization. If that is fine, if it is very finer, then we will get then we will get more finer optimal solutions. But however, that may increase the computational time, or sometimes it may also results in some other issues like loss of dimensionality in terms of dynamic programming. So it's a final allocation for each frame with respect to the queue. So this hill climbing approach leads to optimal allocations only if all the net benefits with sum is being maximized or concave. So only when the objective function is of concave type, so we can use that hill climbing approach. That is, the marginal benefit decreases with the increase in the allocation. It's a concave type problem. So otherwise, only a local optimal solution can be guaranteed. Again, that's another that's one of the limitation of this hill climbing method. That's the same for even calculus based optimization algorithm. So another method which is widely used for non-linear type of optimization problem is branch and bound method. Actually, this branch and bound method is mostly used for the mixed integer linear programming problems. Because of this simplicity, it is also used for solving most of the non-linear optimization models. This branch and bound method is very effective in solving mixed integer linear and non-linear programming problems. The method was originally developed by Land and Doyle to solve integer linear programming problems and was later modified by Dakin. Subsequently, the method has been extended to solve nonlinear mixed integer programming problems. So let us consider this following formulation. Let our objective function be minimization type, that is minimize f of x, which is a nonlinear function, subject to g of j of x is greater than or equal to 0, where j equal to 1 to up to m, and the h of k of x equal to 0. This is equality type constraint. The first one is the non-equality type constraint, and then the third one is the x of j is a integer. So actually, this is branch and bound method is mostly first it was implemented for solving the mixed integer linear programming. So it's one of the constraint. The decision variables are integers. Okay. Here x is a decision vector. So basically that contains the decision variables. If you consider only the first two constraints, that is the equality constraint and the inequality constraint, then that is called this design vector x is called the continuous feasible solution if it satisfies the first two conditions constraints. If the design vector x that satisfies all the constraints, then that is all the three constraints, both the equality, inequality, and the last constraint, that is x is an integer, then this design vector can be said as it's an integer feasible solution. So in this branch and bound method, it involves the enumerating all the integer points, discarding the infeasible ones, evaluating the objective function at all integer feasible points, and identifying the points that have the best objective function value. Although such an exhaustive search in the solution space is simple to implement, it will be computationally expensive even for moderate size problems. The branch and bound method can be considered as a refined enumeration method in which most of the non-promising integer points are discarded without testing them. Also, the process of complete enumeration can be used only if the problem is an all programming problem. For mixed integer problems in which one or more variables may assume values, the process of complete enumeration cannot be used. So mostly this branch and bound method can be used only when all the variables are integers. So in the branch and bound method, the integer problem is not directly solved. Actually, the method first solves a continuous problem obtained by relaxing the integer restriction on the variables. So this is the first step in the branch and bound method. In branch and bound method, without considering the last constraints, that is all the decision variables are integers. Without considering that constraint, the problem is solved by any technique, any linear programming technique. If the solution of the continuous problem happens to be an integer solution, it represents the optimum solution of the integer problem. So otherwise, at least one of the integer variables, say x of I, must assume a non-integral value. If x of I is not an integer, we can always find an integer x of I such that x of I is in between these limits. Once we formulate this condition, we can categorize this into two problems. That is, two subproblems can be formulated, one with the additional upper bound constraint, and the other one is the with the lower bound constraint. So the process of finding these subproblems is called branching. So basically, in branch and bound problem, we are dividing the problem into two types, and that process of division, separating the problems, is called branching. The branching process eliminates some portions of the continuous space that is not feasible for the problem, while ensuring that none of the integer feasible solutions are eliminated. Each of these two subproblems are solved again as a continuous problem. The solution of a continuous problem forms a node, and from each node, two branches may originate. The process of branching and solving a sequence of continuous problem is continued until an integer feasible solution is found for one of the two continuous problems. When such a feasible integer solution is found, the corresponding values of objective functions become an upper bound on the minimum value of the objective function. At this stage, you can eliminate from further consideration all the continuous solutions whose objective functions values larger than the upper bound. The value of the upper bound on the function is updated whenever the better bound is obtained. Actually, if our number of decision variables are quite less, easily we can solve the any optimization problem manually. If it is only less than 2, if it is only 2-dimensional, if it is less than 2, then in fact we can easily use the graphical approach, or manually we can solve it. But most of the real life problems, most of the real world problems, that will have n number of objective functions and also have a number of constraints. So when in that case, our matrix, if you formulate the that canonical form of optimization problem, that matrix, that will become very big. So that matrix we cannot solve manually. So in that case, to look at various tools that may aid us in helping the optimization problem. So like that, we have tools are available for solving the optimization problem. So I have used one such type tool to solve a real world problem. So that's what about this case study. So in this case study, I'm going to discuss about the optimization of Koyana hydroelectric project. So here, this hydropower production is a nonlinear problem. So this we have solved using, first we formulated the optimization problem. That's a mathematical formulation. And then we solved that mathematical formulation using a software called Lingo. It's having various solvers are there. We have used the global solver, which is also having a capability of solving the nonlinear problem. So here, schematic sketch of the Koyana hydroelectric project. This Koyana hydroelectric project is one of the important hydroelectric project in Maharashtra, because it's having highest installed capacity of hydropower plants. If you look at the system, it shows a part of the reservoir here. So actually Koyna Dam is somewhat here. This is where the Koyna Dam is there. This Koyna hydroelectric project, this Koyna Dam is in the upper reach of the Krishna river basin. In fact, this is the first reservoir, first dam in the Krishna basin. Okay. It's a very small reservoir with its catchment area is equal to 891 kilometers square. The system is in such a way that on the western side there are naturally available head is there. Okay, on the western side, and immediate to that, here on the western side you have the naturally available head is there. So the major power plants of this reservoir are situated on the western side, and immediately after that we have the Arabian Sea. Whereas on the eastern side, it's having the irrigation command area and the downstream reservoirs and further basin downstream of the basin. That Krishna basin is on the eastern. Since this western side is having a naturally available head, the major power plants of this reservoir are situated on the western side of the reservoir, and these power plants are underground power stations. Okay, so we have named those power stations as PH1, PH2, PH3, and PH4. So this PH1 and the PH, here the powerhouses are developed in different stages. That is stage 1 and stage 2. Both stage 1 and stage 2 are located in the same underground plant. So we have named that as PH1. And then stage 3, actually stage 3 is also an underground power station, but that is coming under the Kolkewadi Dam. Kolkewadi Dam is another small reservoir. It's just a balancing reservoir. The tailwater from the stage 1 and the stage 4 is taken to the Kolkewadi reservoir, and from using that tailwater and the available head, the power is produced at the stage 3 power plant. And then we have one more small powerhouse at the dam foot, that is mentioned as Koyna Dam Powerhouse, KDPH, and we have mentioned that as PH4. Recently, they have also constructed one more powerhouse on the dam foot, that is on the left side. That's a recent addition to this system. Anyway, that is not considered in this study. So the power for the study purpose, I have mentioned the powerhouses as PH1, PH2, PH3, and PH4. So it's having this Koyna hydro project. It is having two systems. One is Koyna reservoir, and another one is the Kolkewadi reservoir. And the powerhouses are developed in 4 stages, as I mentioned earlier. So the total capacity of these power plants works out to be 1,960 megawatts. These are some of the silent features of the Koyna and Kolkewadi reservoirs. So Koyna reservoir serves both hydropower production and also partly for irrigation purpose. Kolkewadi reservoir is it's a balancing reservoir. It just regulates the tailwater from the stage 2 and 3 powerhouses to the Kolkewadi powerhouse. It's a simple balancing reservoir that you can infer from the storage capacity of the Kolkewadi reservoir. So the storage capacity, the gross storage capacity of the Kolkewadi reservoir is only 36.22 million meter cube, whereas the storage capacity of this Koyna reservoir is 91.40 million meter cube. So this gives the idea of how big the Koyna reservoir is and how small the Kolkewadi reservoir is. So Kolkewadi reservoir is just a balanced reservoir, and other hydraulic particulars are given here. Net storage of is 2652.40 million meter cube, whereas Kolkewadi is 11.22 million cube. And the water spread area at the full reservoir level is 115.35 kilometers square. whereas for Kulkewadi reservoir it's 1.67 kilometer square. So here maximum water level, full reservoir level, minimum drawdown level, and various other features are given. These are the details of the powerhouses. So stage 1 and stage 2, they are housed in a single unit or in a single plant. So we have taken it as a single unit as PH1. So it's having 4 turbines in both stage 1 and stage 2. It's a total capacity of the turbines is 4 turbines of 70 megawatts in stage 1 and 4 turbines of 80 megawatts in stage 2. And this stage 3, which is comes under Kolkewadi Dam, we have named it as PH2. There we have 4 turbines of 80 megawatts. And stage 4 is the biggest power plant in the system. It's having 4 turbines of 250 megawatts. And all these PH1, PH2, PH3, all these 3 power plants are on the western side of the reservoir, whereas this Koyana Dam powerhouse is on the dam foot. Actually, the water flows to the eastern side from this way. Okay, so since the major power plants are located on the western side of the reservoir, western side of the dam, in fact, that has resulted in the conflict in using the available water. So if you want to generate more hydropower, then major share of the water need to be diverted to the western side. In fact, that resulted in the dispute among various states that shares the Krishna water. So according to Krishna Water Dispute Tribunal, that has limited the diversion of water towards the western side for power production. So this figure shows the inflow into the Koyana and the Kolkewadi reservoir. So the complexities are the hydropower releases are termed as non-consumptive, since the water is used for some other purpose after power generation, mostly for irrigation. However, in case of Koyana hydroelectric projects, the releases to major powerhouses and irrigation are in opposite direction, which makes the operation of the system very complex. So diverting the large of water to major powerhouses on the western side of the reservoir resulted in dispute among different stakeholders. The Krishna Water Dispute Tribunal limited the diversion of large quantity of water towards the western side for power production, and also there exist conflicts among all the powerhouses, since the powerhouses are different and have different capacity of power generation. So considering all these complexity that exist in the field, we have to develop a suitable optimization model for maximizing the hydropower production from the system. So we developed a model. So before developing an optimization model, we studied the existing operation of the hydropower plant by developing a simulation model. Actually, this Koyana hydroelectric project, it's a peak power plant. That is, it is operated only for producing peak power demand. In power production, there are 2 categories are there. One is base load and another one is the peak load. Mostly these hydropower plants are operated producing the peak loads, because we can easily increase or decrease the power production in hydropower generations when compared to other mode of power generations. So again, this Koyana system is also a peak load system, which are operated only for few hours of duration in a day. So we try to simulate, we try to study the existing operation policies of the system using a simulation model, and we simulated the operations for different durations, that is for 4-hour duration, 6-hour duration, and 8-hour durations. And also we consider 2 scenarios based on the Krishna Water Dispute Tribunal constraints, that is being a limitation on the water. So according to Krishna Water Dispute Tribunal, we cannot divert huge quantity of water for power production towards the western side. So that constraint we have considered in two cases. One is strictly following by that condition, and the other one is without following that constraint. And we use these statistical performance indices such as reliability, resilience, and vulnerability to estimate, to assess the performance of the system. So using that simulation model, we found that the power production increased up to 12%, or the 12% increase in releases to the western side process for 4-hour duration of operation. And the reliability indices shows that the system is more reliable for case 1, that is 4 hours operation of powerhouse for studied. The high resilience and the low vulnerability indices show that the power production is so stable and continuous for case 1, that is for shorter duration of operation. So with this background, we developed the optimization. So here the objective function of the optimization model is maximizing the hydro production from all the 4 powerhouses. So that is given here. Maximize Z equal to summation of T equal to 1 to 12 and N equal to 1 to 4 pH N comma T. So pH is nothing but the power production, and here N represents the number of hydropower plants. So we have grouped that into 4 plants, pH 1, pH and pH 3, pH 4, and T represents the time period. So it's a monthly model. So T represents month, time period 1 to 12. So pH of N comma T is the power produced from the powerhouse N during the time period T in of kilowatt hour. So according to Louds et al. 1981, power production during any time period T this depends on the installed plant capacity, flow through the turbines, and the average effective storage head, number of hours of operation, and a constant for converting the product of flow, head, and plant efficiency to electrical energy. So accordingly, the power production function is given like this: pH equal to K is the constant, which is used to convert the hydropower into kilowatts hour, where R is the release to the powerhouse, and H is the net head, and neta is the plant efficiency. The average head available during a particular time period T is expressed as a function of storage. So then the net head is estimated by deducting the tail water level and the frictional losses. So here the objective is to maximize the power production from all the powerhouses of Koyana hydroelectric project. So this is subjected to various constraints. So we have considered all the physical and other constraints. First, the constraints related to the power plants. So each power plant have some requires some minimum head for its operation. If the head is below that limit, then we cannot operate the power plant. So that is given by the minimum drawdown level. So the water level in the reservoir is goes below the certain level, then we cannot operate the hydropower plant. So that we have, that constraint is imposed as minimum drawdown level constraint. And then maximum power production constraint. So if such a constraint is not imposed, then what this optimization model that will actually release excess flow to a power plant, and actually that will generate more than the capacity installed. So to control that, we have imposed a constraint known as maximum power production constraint. This is more specific to the power plants. And then we are also having another constraint, which is in terms of Krishna Water Dispute Tribunal. So according to Krishna Water Dispute Tribunal, we cannot divert more quantity of water towards the western side for power production. Actually, that is given by this constraint. That is the sum of water released for power production towards the powerhouses in the western side. That should be within certain limit, that limit imposed by the tribunal. So that constraint is given. At the same time, we have to also satisfy the irrigation demand. So that's again given here. And these irrigation releases should be greater than or equal to the irrigation demand. And physical constraints, water balance equation for Koyna reservoir and Kolkewadi reservoir. So the first equation is for the Koyna reservoir. So the final storage at the time period, at the end of the time period, should be equal to the initial storage at the beginning of the time period plus inflow minus the releases to powerhouses minus the overflow from the reservoir and evaporation losses. And this is for the second equation is for the Kolkewadi reservoir. So for the Kolkewadi reservoir, the tailwater from the powerhouse 1 and powerhouse 3 are the inflow to the reservoir. So that's why this R1 and R3 that is added in the water balance equation of Kolkewadi reservoir. And then steady state, we have also considered the steady state condition. And then we have given the storage constraint and overflow constraint. In addition to this, we have also given the non-negativity constraints. So all the decision variables are greater than 0, greater than or equal to 0. So once the optimization model, this mathematical model is formulated, so we have formulated the mathematical model with the objective function and considering all the field constraints. Once it is formulated, then we have to solve the optimization model. Solving that model, actually we analyzed 4 policies, 4 scenarios. That is, the first scenario is no binding constraint on the western and eastern side releases. That is, we have not considered this constraint, this release constraint. We have not considered any release constraint on the power plant. So that's a no binding constraint on eastern and western side. This is just to know the what is the potential available for power production. What's the optimal hydropower production that can be obtained without any binding constraint on releases, both on the western side as well as on the eastern side. And the second policy is just considering only the annual binding constraint on irrigation. That is, we ensure that the at least the irrigation demand, total annual irrigation demand, are satisfied every year. So that's the second policy, to ensure that total annual releases are satisfied every year. So that is the second policy. When we were doing like that, we have found that though the annual irrigation demands are satisfied every year, but however, if you look monthly wise, the demands are not satisfied. And some of the months the releases were less than the demand, and some of the months the releases were more than the demand. So monthly wise, the demands are not satisfied properly. Hence, to ensure that both the annual as well as the monthly demands are satisfied for irrigation, we developed the policy 3. Both the monthly and annual binding constraints are on irrigation are considered in policy 3. And the final one, the policy 4, strictly enforcing all the constraints on releases. On the western side as well as on the eastern side, considering all the binding conditions. So actually that shows the exact operating condition of the Koyna hydroelectric power plant, considering all the constraints. That is, we cannot release excess water on the western side for generating maximum power like that. All that Krishna water dispute constraint, that is also considered in the final policy. This model, this optimization model, and for these 4 different scenarios, for the 4 different operating policies, were solved for 3 different inflow situations. There is one for wet inflow, that is 50% dependable inflow, and one normal inflow, 75% dependable inflow, and another one for dry inflow conditions, that is for 90% dependable inflow. This nonlinear programming optimization model is solved using global solver in Lingo software. So this global solver combines a series of range bounding and range reduction techniques, which is within a branch and bound framework to find the global optimal solutions to non-convex and nonlinear programming problems. So here, this global solver, it uses the branch and bound method in a slightly more fashion to find out the optimal solution. So these are the results obtained from the model maximum power production, that is annual power production. So if you look at the figure, 4 policies, the policy 1 mentions that there are no constraints on releases for power production as well as for irrigation. Policy 2 that shows the constraint on annual irrigation releases, so that the demands are satisfied annually as per the requirement. And then policy 3, both annual and monthly irrigation constraints. Policy 4 is strictly based on the Krishna Water Dispute Tribunal. So when we enforce, when no constraints, no binding constraints are considered, obviously the model has resulted higher hydropower generations. Also, one trend you can observe here, when strictly the Krishna Water Dispute Tribunal constraints, that the binding constraints on diverting the water is strictly enforced, you can see that almost scenarios, wet and normal scenarios have almost resulted in the same hydropower generation. And more difference among 3 different inflow scenarios is also quite less when compared. That means the inflow don't have that much effect here. Okay, but on the other hand, with the change in inflow scenarios, the power production also varies significantly. So among these policies, the policy 1 has resulted in a maximum power production of 5826.29 million kilowatts hour for wet inflow scenario, since there is no restriction on the western and eastern side releases. These are the production values for definition, and this is for the wet inflow scenarios. Again, for different power plants are given. So the bottommost one is for power plant 1, and the second region is for power plant or powerhouse 2, and third one is for powerhouse 3, and fourth one is for powerhouse 4. This is for power. So if you look at the first graph, so here we have not imposed the constraints on the releases. So obviously this policy 1 has resulted maximum power generation. But you can see that this powerhouse 3, this powerhouse 3 has resulted in maximum power generation. That's the biggest power plant in this. So that has resulted in maximum hydropower generation. This powerhouse 4, which irrigation releases are made. So actually, that has the model has very less releases, and in fact no releases in most of the months, because it's a power plant with a small power production capacity, and of that, what happens if you are not enforcing any such constraint? Since it's a maximization type of problem, the model ensures only the maximum production and not the has not given any significant irrigation. So to ensure that significant irrigation releases are made according to the demand, we have specifically considered 3. So that is this one. So if you look at this figure, you can see that in all the months, you can see the power releases, corresponding power production through the powerhouse at the dam foot. And the policy 4 is for strictly enforcing the Krishna Water Dispute constraint. Strictly we consider the binding constraints on us towards the western as well as the eastern side. So these all figures are for wet inflow condition. the same for normal inflow as dry inflow conditions. It releases to different power plants in the system for different policies and inflow scenarios. And these are the final resulted storage curves for the reservoir for different policies. And one thing what we have observed is almost all the policies, all the scenarios have resulted the same storage level for the Kolkewadi reservoir, because Kolkewadi reservoir is just a balancing reservoir, just receives the tailwater from the powerhouses of Koyna reservoir and regulates the flow to the other powerhouse, which is situated at the downstream of Kolkewadi reservoir. So because of that reason, almost all policies, all scenarios have resulted in the same storage level for the Kolkewadi reservoir. So we have the optimal solution here. So after obtaining the optimal solution, we have to check whether that optimal solution is sustainable for longer time period. So to check that, what we did, we simulated that optimal solution. We simulated the operations of this Koyan hydroelectric project for that optimal solution, and then we studied the performance of the system. Upon doing that, we identified that the system has satisfactorily performed well for a longer time period using the obtained optimization model from the optimization model. Actually, we simulated the policy 3. So the C3, which has satisfied both the irrigation demands, month-wise irrigation demands, and has also resulted in considerable hydropower production compared to policy 4. So we took the policy 3 as the implementable, and we simulated the those optimal policies of policy 3 using the simulation model. So in that, we studied various indices like mean frequency, monthly frequency irrigation deficit, annual frequency irrigation deficit, annual average irrigation deficit, percentage annual irrigation deficit. And again, we simulated this model or these policies for different inflow scenarios. One is wet inflow scenario, dry inflow scenario, and normal inflow scenario. So you can see that almost all policies, the policy 3 has performed well, quite well for these 3 different inflow scenarios. And in fact, the failure is also quite less. Only in few months it has failed. And if you look at the percentage failure, that is even less than 10% the requirement. So when you compare with the storage of the Koyna dam, this that is 74.97 is the maximum deficiency resulted, it's annual average irrigation deficiency resulted by the simulation model. When we compare this deficiency with the storage of the Koyna reservoir, it's quite less. Okay, so we can say that the optimal solutions or the optimal policies obtained from the optimization model performs well for even for longer time period in the future. So from this study, we concluded that among different dependable inflow conditions, 50% dependable inflow level have resulted in more power production due to high inflow. The model resulted maximum power production of 4824.48. Oh, this is multiplication sign. There is some formatting error is there. 4824.48 million kilowatts hour when there is no restriction in releases. It is observed that the increase in release for irrigation has decreased the power production considerably. This study shows that the power that can be produced with all the release constraints is only 55% of the power production potential of Koyna reservoir. The developed model has also resulted in good storage at the end of the season, and available storage can be further utilized for more hydropower generation. So with this, I conclude my If you have any questions, you can ask me or you can type it in the chat box.
Hello.
Yes, sir.
If any questions are there, participants can write in the chat box. Or even you can write in question and answer.
The reservoir is only for irrigation purpose. Which technique can be used? Again, if it is only irrigation purpose, means if it is a simple linear problem, sometimes a linear programming technique may result in a global optimal solution itself. So in that case, you no need to go for a complicated or a very complex techniques. That incremental value again, it's only on users thing that if you take more finer values, actually our problem will give a better net benefit. At the same time, if you go for larger incremental value, then the end allocation as well as the net benefit may not be a more accurate one. Actually, there is no hard and fast tool to fix that increment. Basically, these are all the deciding parameters. So that can be fixed only on sensitivity analysis. So we have to check with the different incremental values, and based on the net benefits only, we can fix that incremental value. So not only in this type of optimization problems, even if you are using some evolutionary algorithms, there are many parameters which defines the working principle. In all those parameters, we have to do certain sensitivity analysis. So here also, this incremental value can be better if you fix those using some sensitivity analysis.
So we have a question.
Yes.
Does soft techniques also incorporate stochasticity like SDP?
Actually, if you look at the literature, that's in fact I discussed this point. These soft computing techniques have inherent randomness in its algorithm. So there explicitly it is not considered. If you take the stochastic dynamic programming or if you take the dynamic programming, we can consider the randomness either implicitly or explicitly. Okay, so that's why it's called stochastic dynamic programming. But if you look at the soft computing techniques, mostly the authors or the researchers, they won't explicitly consider the randomness there, because the algorithm itself is random. In each and every process, it is having a random parameter. So that randomness is inherently included in the algorithm. So there, usually it is not considered explicitly. Is it clear?
Yeah, questions are over.
Some questions are there in chat box.
Okay.
Can we determine the optimal mapping pattern with respect to releases can be done using nonlinear programming. So it depends on the objective what you are framing. If your objective is very linear one, there is no need for a nonlinear programming. Okay, it's all depends on the type of objective functions. And in fact, many people are formatting different types of objective functions. So it's basically depend on the objective functions and constraints. I think this Ajim shared your question is related to branch and bound method. Yes, branch and bound method is basically that is developed for mixed integer programming. So we have to consider that constraint. It has to be an integer value.
Yes, sir. Questions are over.
I think I have answered all the questions in chat box.
Okay. Okay.
That is one question. Sir, I need to allocate good channel for communication. Which optimization technique is good? I don't know. It's not related to my field. I don't know. Is it
Yeah,
related
that
to
is the communication engineering. That is from
Uh,
communication engineering.
So the technique, we have to select the technique based on our model. First, we have to frame our model with objective function and constraints. Only looking at that constraint, whether it is linear, non-linear, concave, convex. So looking at that only, we have to then go for selecting a particular optimization technique. So that's what my answer is here. And this is especially for conventional techniques. And if you are going for a recent subcomputing based techniques, then any technique can be applied.
One more question is there in the first step of hill climbing problem. When no allocation is made, how will be the benefits, sir?
That the benefits are zero. That's what if you look at the problem, first three steps were combined it together because it actually didn't satisfy the condition. The release Q has to be greater than Q max. It has not satisfied that condition, or the Q should be greater than R, that river flow. Okay, so until it satisfies that condition, the releases are not made. So that's why here the problem what I explained, the first three steps are combined. How validation is done for RO problems. RO means what you are meaning, reservoir operation or
Reservoir operation.
Okay, so usually that's what in fact in my study what I did, first I developed a simulation model and I compared my results with the actual releases, what it was done by the dam operators. So this gives some idea whether our model is perfect or not, whether our model actually replicates the scenario or not. Okay, once you are getting the matching results, then okay, you can say this is okay, we have correctly captured the field condition. then you can go for a further thing. So that's related to simulation. In fact, for optimization also, optimization is here we cannot validate our model. We can compare our results with the one which is practiced in the field, but obviously things will be different. Here in optimization, only thing we have to check is whether whatever results we have obtained is global optimal solutions or local optimal solutions, and we are trying to satisfy all the constraints, whether all our constraints are satisfied or not. But if you want to validate that can be validated only with the simulation model. In fact, I thought of introducing the simulation concepts also, but I didn't expect that I will take 2 hours this itself.
Yeah, Vensim, actually you wanted to introduce.
Yeah.
Okay, I think questions are over. There are no more questions. So should we end, Arun Kumar?
Yes, sir. Actually, I have to thank you for giving me this opportunity. It's a wonderful experience, this one, sharing my research and my knowledge. And I am happy that there are many questions are here. So the audience are very active in this program. That's a positive sign.
So on behalf of our institute and department, I thank Professor Arun Kumar for sharing his optimization knowledge and whatever he has worked in nonlinear programming. So thank you very much, Arun Kumar.
Thank you, sir.
For joining with us. Thanks a lot.
Thank you, sir. Thank you, sir.
For
I also thank
participants,
all the participants for their active participation.
Yeah. And for participants, the next session will be as per schedule at 1 o'clock. And at 3:30, please join 5 minutes early at 3:30, because from 3:30 to 5 o'clock, your examination will be there. Okay. So now next session is at 1 o'clock. So please join within time. Thank you very much.
Thank you, sir.
Yeah. So some network issues, I think. Hello.
Hello.
Yeah. Okay. So
Yeah. You can let me know when should I start, so I can.
Yeah, immediately.
Yeah.
Pushpak.
Yes, sir. Okay, so I welcome all the participants for this session. For this session, we have with us Dr. Lalit Kumar Singh. Sir has received his PhD degree from Indian Institute of Technology, Banaras University. He is currently scientist in Bhabha Atomic Research Center, Department of Atomic Energy, Government of India, since last 20 years. and has distinction of working on pressurized heavy water reactors and light water reactors. He is an expert in a number of industrial policy formation of IIT Roper, US for many autonomous institutes, and member on the advisory board of many institutes, universities. He is supervising many PhD students of different IITs, NITs. He has published several research papers in journals of high impact factor like IEEE transaction, IEEE computer, ACM, etc. He is a reviewer of several SCI indexed journal of high impact factor. He is a member of editorial board of many reputed journals and guest lead editor of many special issues. He has been invited for chief guest keynote speakers session and talk in many international conferences, short-term courses, workshops from many IITs, NITs. He is recipient of many awards like Publication Award, Group Achievement Award, etc. He is a life member of Indian Nuclear Society. He is also faculty of Nuclear Training Center, Department of Atomic Energy, Government of India. He is interfacing with other countries like Russia, USA, France, etc. for importing nuclear reactors that are based on new technologies. His research interests are in the area of reliability, safety, and security of safety critical computer-based systems. So far, he has completed 33 projects of Department of Atomic Energy, Government of India. Welcome Dr. Lalitkumar Kumar sir for this session.
So I welcome Dr. Lalit Kumar Singh for this session, and we will be blessed with his experience in PARC. He is a scientist, and even I request him while session is on, you can make your video on.
Okay. Yeah.
So that the participants will see. And please start the session.
Yeah. So I think I'm not able to share the screen. So you need to give me the privileges so that I can share the content. Yeah, now it is. So thank you, Professor Ragulvar and all our organizing committee members who had provided me this opportunity to share some of the experience to all the participants. And so to start with, let me share my slides. So I think the slides are visible.
Yeah, slides are visible and you are audible. Please continue.
Yeah. So I'll be talking on safety analysis of mechatronic systems. So first, let me introduce you about the subject and on what is the essentiality of this topic and what is the significance of this topic in the industries. So when I talk about the mechatronic systems, it contains, the mechanical component also and the electronic components also. And mechanical means, for example, the actuators and all the mechanical devices, which are basically, controlled by the computer-based systems. Like that also contains the electronic software components. And there are the various safety critical systems that are widely used in the industries, which are mechatronics in nature. And safety critical systems are those systems, the failure of which can lead to the catastrophic disasters, or even it can lead to the loss of human life. And hence, the safety analysis is very essential to analyze for such kind of systems. And the example of these systems are, for example, like nuclear industry or aerospace industry, medical industry, automobile industry, defense industry, military industry, where we make the use of such kind of systems. And these are the important critical infrastructure of the country, and hence it is very much essential to perform the safety analysis of such kind of systems. Now, coming to safety, like what does safety means? Safety in the sense we have to identify the risk associated in the system. And so first one is in the safety is identification of the risk, and the other one is the mitigation of the risk. If some risk has been identified, what is the process through which we can mitigate the risk? So I'll be talking on particularly, I mean on both the things, the identification as well as the mitigation. So to let us go, let us see the today's outline quickly before we go to the real content. So first we will give the introduction, although I have covered up the basic background of the safety. Then I will be talking on the battery nets, which is a mathematical formalism. And basically this battery net was introduced, this is a mathematical modeling technique which was introduced by a PhD researcher, a German PhD researcher known as CA Battery in 1960s. And basically he introduced this concept to model the stochastic behavior of the system, or to model the stochastic processes. So coming towards the processes, we can easily categorize the processes into two parts, two types. One is deterministic processes, and the other one is the stochastic processes. So the deterministic processes are those processes the outcome can be 100% guaranteed. For example, suppose I do have a pen in my hand, and if I drop a pen, I can 100% guarantee like it is going to fall down on the earth. Why? Because of the gravitational force that is acting on that pen. So what I mean to say, where I can guarantee the outcome of any process, such process is known as a deterministic process. And the processes whose outcomes cannot be guaranteed are known as stochastic processes or probabilistic processes. And like all the human-made processes are stochastic in nature, because human itself is probabilistic in nature. So, for example, let's try to understand with the help of a very realistic example. Suppose I want to attend a meeting in Hyderabad at 5 p.m. for which I need to catch the flight from Mumbai at 1 p.m. So considering all the traffic delays, the local traffic at Mumbai, at Hyderabad, and the aeroplane delay, the flight delay. So all these worst case, if I consider and then I plan, then also it may be there is a possibility that I may lose the flight. And the reason could be manifolds. The reason could be, for example, in the local Mumbai local traffic was the worst, and I had to take the alternate path, and the normal path was blocked because of some road construction, and for that I'll have to take the longer path. Or the flight got delayed because of some unavoidable circumstances, or it may get cancelled also. So what I mean to say, in spite of rigorous planning, I cannot 100% guarantee like I'm going to accomplish this task, right? Or there could be the road accident or whatever the worst scenarios that could happen, which has a potential to, miss my schedule. All the processes which are made by human, it means all the industrial processes are stochastic in nature. And in 1960s, basically the people were striving to introduce some of the effective techniques which can, model the dynamics of the process or the stochastic behavior of the process. So Petri nets is one of the mathematical formalism, and it is a very good graphical as well as mathematical tool. So we will talk more about this Petri nets along with the history of the Petri nets. And then I will also show how we can use this Petri net model to model any system, for which I'll be taking a case study, and we can see like how the case study can be modeled using the Petri nets, and then we can perform the safety analysis, in which I told you first of all we will try to identify the risk, what are the associated risk in the system, and then I'll try to find out some way to mitigate those risks, and then we can conclude our session. We know like the computers are now being used in every domain in day-to-day life, and to solve or to control or monitor all the industrial systems, irrespective of what kind of systems they are or irrespective of the domain. And these are used for, monitoring purposes as well as the controlling purposes. And if they are being used for the monitoring purposes, they are used as a passive component, or if they are used for controlling purposes, they are known as the active components. And as I said, there are various industries, important industries, which make the use of these computers, for example, power plants, aerospace, medical domain, etc. Okay. So definitely when we will do the modeling, we have to model the software as well as the hardware, because both failure is important, and they both will be responsible to contribute a risk. So we have to analyze both the components, and it is important to stress the system in nature, so that we can find out under stress condition how your system is going to behave. So one interesting fact that we can emphasize on, that software does not harm anyone. But definitely software has a power to control the hardware through some electronic relays, and hence and only the hardware which can damage the things. Hence the software safety must also be considered as a part of the overall safety, because ultimately all the hardwares are basically being driven by the software. Now coming to the Petri nets, as I talked, this is a mathematical and graphical model, and the concept was introduced by C.A. Petri. And why graphical model or graphical tool? Because it has a modeling capability to represent the behavior of the system or to represent the dynamics of the system. And basically, this will help to all the stakeholders in their respective domains. For example, if I'm a businessman, I want to outsource a project, and I write the specifications, but we know, like, the error gets introduced from the requirement specification, may introduce from the requirement specification itself if there is some ambiguity in the requirements, or the client is not able to understand the requirements properly, what I want, and he is implementing something else. So what he can do, if I suppose outsource a project to any organization, he can basically model the system using this factory nets, and he can model the runtime behavior also, which can be shown to me, and I can find out at that time whether all the functional requirements have been taken care of. And in any case, in case something is missing, I can point it out, and the things can be rectified there itself. So, or for example, if I'm a tester, then I can understand, okay, what's the dynamics of the system, what is the runtime behavior, and accordingly I can design the test cases to test the system once the development of the system gets completed. And it is a very good mathematical tool also, because we can embed the mathematical knowledge, and we can solve the various algebraic equations or the state equations to know more and more insights, of the system, or to know more and more dependability attributes of the system. So specifically in this session, we'll be talking on the safety, which is a very important, dependability attribute, especially if we are dealing with the safety critical systems. So it is a best communication, between the theoreticians and the practitioners. Now let us go through a brief history of the factory net, just to understand why, the basic milestones that this factory net achieved, and the reason of this popularity. So, as I said, in 1962, C.A. Petri introduced this concept in his PhD dissertation, who was a German PhD scholar. And, after going through the thesis, the people were appreciating, and that time in 1970s, there was an era where the development on the concurrent systems or the parallel systems were very on the peak. And so MIT USA was trying to explore this factory net formalism to identify whether it can be useful to model such kind of applications which are concurrent or parallel in nature. And with this objective, in 1970, MIT USA conducted a conference on concurrent systems and parallel computation. And the conclusions were very beneficial, and the people were trying to find out or increase the capability of the model. So they were trying to explore Petri nets in the deep, and what could be the related methods. And with this objective again, they decided to meet in 5 years later. So in 1975, MIT USA again conducted a conference on Petri nets and related methods. And then it gains, a huge popularity in the industries, and where the industries were using Petri net for the modeling purposes at least. And they had to train the people for 3 to 4 months, and looking at the demand, looking at the industrial demand, Germany started a course on general net theory of processes and systems. And then the people from different domains were also trying to explore this construct to, find the possibility whether this modeling construct will be able to, model the application of their particular domains. And with this objective, it diversified people from different domains gathered together. And in the France, when first European workshop on applications and theory of the Patrinet was conducted. And thereafter, the people were, or the researchers were coming out different with different flavor of the Patrinets. For example, if I want to work on the real-time systems, definitely the timing information plays a very important role. And for that, there should be a Patrinet where we can embed the timing information, and that that the flavor of that particular Patrinet is known as timed Patrinet, and for which an international workshop was conducted in 1985 in Italy. And so this is not an exhaustive list, but it covers some of the important milestones just to have an idea from where it got popularized and how this was started, being used in the industries to solve more and more challenging problems or the industrial problems. So if you look with respect to the applications, what kind of applications it can cater. So it can cater almost every kind of applications like fault tolerant systems, data flow computing systems, multiprocessor memory systems, control systems, safety systems, and a lot of dependability attributes can also be quantified, like performance, reliability, safety. Such kind of dependability attributes can also be quantified using such Patrinets. Now let us look on the working principle of the Patrinets and what are the basic constructs of the Patrinets, what are the basic building blocks. And just to be aware on these aspects, I have considered a very small chemical reaction. To understand the working mechanism, and then we will take the real case study to model, that particular case study using Patrinets. So, for example, suppose I want to model a very basic chemical reaction that is hydrogen and oxygen that gives water. And so first, so this figure, if you are able to see this figure, it is a Patrinet figure. So first, let me start with the building block, and then I will explain, the modeling part. So if you are able to see, there are the three big circles in this figure, and these three big circles are known as places. So there are the three places. I'm representing. I have taken the three places: one to represent hydrogen, one to represent oxygen, and one to represent water. Now the next building block is the rectangular bar, which is known as the transition. So there is only one transition in this figure, which is represented by T, and the places can be connected to the transitions, and the transitions can be connected to the places. with the help of the directed arc, but there cannot be direct connections between the places and or between the transitions. So in this figure, you can see the arc which is connecting the hydrogen place and transition T. There are the three arcs. One is connecting hydrogen place and transition T. One is connecting oxygen place and transition T. And one is connecting transition T and water place. And these arcs can be input arc or the output arc. So the entity from which these arcs are originating, for those entities, these arcs are output arc. And the entity on which it is terminating, or these are terminating, for those entities, these arcs are input arc. For example, in this figure, for hydrogen place, there is only one arc which is connecting, to the transition T. For oxygen place, there is one arc which is connecting to the transition T. And from the transition place, there is one output arc which is connecting to water place, and two input arcs which are coming, one from hydrogen place and other from oxygen place. Similarly, for water place, there is a one input arc which is coming from the transition T. So now the next important building block is the weight of the arc. If you are able to see the numeric number that is assigned on each of the arc, that numeric number is known as weight of the arc. So, for example, the arc which is connecting hydrogen place and transition T contains the weight 2. The weight of the arc which is connecting oxygen place and the transition T, I have not put any weight, so by default it is treated as 1. So or either you can put it as a numeric 1. And the weight of the arc which is connecting transition T and the water place is known as is 2. We will see what is the significance of these weights, but currently I am only focusing on the various building blocks. Now, one more important building block is you are able to see the small embedded circles that are inside the places. For example, if you look the hydrogen place, there are the two small embedded circles, and these circles are known as tokens. And I'm using these two tokens to represent the number of atoms of the hydrogen, because hydrogen contains two number of atoms. Similarly, oxygen also contains two number of atoms, so I'm representing it by two tokens. And interestingly, these tokens represent the state of the system. The distribution of these tokens among the places basically represent the state of the system. For example, here the state of the system is 220 because there are two tokens in the hydrogen place, there are two tokens in the oxygen place, and there is no token in the water place. So 220 is the starting state, or sometimes in terms of patching it we can name it as marking. So 220 is the marking. And because it represents the initial state, so it represents the left side of this figure of this reaction, that is 2H2 plus O2. Now it has to be converted into water. So definitely then the state of the state of the system will change. So when I said the state of the system will change, it means the distribution of the token will change. And how the distribution of the token will change, that has some rule. And the rule says that any of the transition in the battery net must be in enabled state. For example, in this figure, there is only one transition T, so this transition must be in enabled state. Now, what is the criteria of the enablement of the transition? So the eligibility criteria of a transition to be in enabled state is that all the input token must contain sufficient number of tokens. IDP, please listen carefully. The enable criteria of the transition is that all the input places must contain sufficient number of tokens. So if I see this transition T in this figure, the input places are hydrogen and oxygen, and these two places places must contain sufficient number of tokens. And who will decide the sufficiency criteria of the token? Here the significance of the weight of the arc comes into the picture. So you can see, like, the weight of the arc which is connecting hydrogen place and transition T is 2. So it means the hydrogen place must contain at least 2 number of tokens. And it is not all logic. Please listen carefully. And the oxygen place must also contain sufficient number of tokens. And you can see the weight of the arc which is connecting oxygen place and transition T is 1. So oxygen place must contain at least 1 number of token. And here this eligibility criteria fulfills, and hence the transition T is in enabled condition. And when any transition T is in enabled condition, it fires. And after firing, the movement of the tokens starts from input place to the output place. But so it means the distribution of the token is going to change, and hence the state of the system is going to change. But how many tokens will be moved out from the input places and how many will be deposited into the output places, that will be again totally decided or governed by the weight of the respective arc. For example, in this figure, the weight of the arc which is connecting hydrogen place and transition T is 2. So after firing of T, the 2 tokens will be moved out from hydrogen. And the weight of the arc which is connecting, oxygen place and transition T is 1. So on firing T, 1 token will be moved out from oxygen place. And so in total, if I sum up the number of tokens from all the input places, the 3 tokens will be moved out from once the transition T fires. And how many will be deposited to the output places? That also will be governed by the weight of the output arc. And here the weight of the output arc is 2. So only 2 tokens will be deposited into the water place. So the next state is like this. So here the 2 tokens have been moved out from the hydrogen place, and 1 token has been moved out from the oxygen place. And although the 3 tokens have been moved out from the all the input places, but only 2 were deposited in the output place. So one noticeable point from this can be concluded that there is no law of conservation of tokens. The moment the removal of the token from input places and the deposition of the token to the output places totally depends on the fate of the respective arcs. And if you look the state of this system now or now, so it has been changed to water, and the state of the system is 0, 1, 2, because hydrogen place contains 0 tokens, oxygen contains 1 token, and water contains 2 tokens. And so after firing T, and now you can see the state, or you can see the enabling criteria of the transition T. So as I said, the enabling criteria was that all the input places must contain sufficient number of tokens, and here the hydrogen place must contain 2 number of tokens because the weight of the arc which is connecting the hydrogen place and transition T is 2, and which is not, so it means it is not fulfilling the sufficiency criteria of the tokens, and hence now it will not change its state, and it has become it has reached to the dead state. So here I want to introduce one more concept known as the reachability graph. And reachability graph says, or it represents the total number of possible states in the system throughout its operational life. So for example, here only the 2 states were possible. One was this state, that is 2 to 0, and after firing transition T, the state was 0, 1, 2. Okay, so only 2 states were possible, and in this way we can draw the reachability graph. We'll see like in the real how we can draw the reachability graph, and we'll be talking taking a case study. Now let us talk about the case study, and I'm taking a case study of a reactor protection system. And a reactor protection system is a complex control system, and which contains several safety electronics components, mechanical components, software components, and which are known as nuclear safety components. And this protection system is used when I want to shut down the nuclear reactor because of or under some emergency conditions. And so first let us before going to the real modeling, we need to understand the system very conceptually. And so first let us try to understand this system. So this is the system pictorial view, and the system mimic, where you can see in the right hand side there is a spherical shaped structure known as calandria, where calandria is written. And in the calandria the nuclear fission reaction takes place. We all know the working mechanism of the nuclear reactor. So what happens, the heavy nuclei, or the element which is having heavy nuclei are used as a fuel. For example, uranium, plutonium, thorium. And so what happens is when the heavy nuclei has a tendency to undergo the spontaneous fission. And when it fissions, some radioactive components gets released. And in one fission, almost 2 to 3 radioactive components gets released, and 2 to 3 neutrons also gets released. Along with that, almost 200 to 20 million electron volt of heat energy also gets produced. And that 2 to 3 neutrons in that particular spontaneous fission will strike individually with the uranium nucleus, and each neutron undergo one separate fission reaction. So it means when one neutron will strike to the uranium nucleus, it will produce the 2 by radioactive components, as well as the again 2 to 3 neutrons, and again 220 million electron volt of energy. And that happens for every chain reaction. So here you can see the neutron population increases exponentially, and hence the temperature of in each reaction keeps on accumulating, and it also increases exponentially. And such a temperature, such a high temperature, cannot be sustained, in the mechanical components, and hence there should be some mechanism which can transfer this heat energy, or it can transform into some electrical energy, so that we can generate the electricity from the power plant. So basically, there are some control systems which are trying to control this fission reaction by controlling the population of the neutrons. And for example, like we do have our control functions inside our body, like heart, or kidneys, lungs. These all are working. These all are the control systems which basically control the various process parameter of the human being, like blood pressure, or oxygen level, or sugar level, heartbeats, etc. And when any of these components malfunction or fail, we have to take the medicines which basically suppress the consequences of the failure of these control functions. Okay, so basically safety systems are those systems which comes into the picture when control systems fail, and when in the control system here, which were responsible to control the fission reaction by controlling the neutron population or the neutron density, that fails, then there is nothing but we have to shut down the nuclear reactor. It means we have to eat up all the neutrons, so that I can ensure like the chain reaction has been terminated, because neutrons were only the responsible guy for the sustaining the chain reaction. And this is the system which does this. And let us try to understand the working mechanism. So here the calandria, where so much of heat is accumulating, and because here the neutron population is there, which is responsible for the fission reaction. So if you are able to see an internal pipe that is passing through the calandria and having very, very tiny holes, basically these holes are to sprinkle the poison into the calandria so that all the neutrons can be eaten up. So we have to put some liquid which can basically eat up all the neutrons, and then liquid, because it is eating up, it is known as the poison. So we have to insert the poison. And if you backtrack this mechanical pipe coming from the calandria, from where it is towards its originating point, you can see it is connecting to a poison tank, in which which is filled with the poison, and it also contains a floating ball which is made of plastic. And that why we have taken the floating ball, because whenever there is a demand to shut down the nuclear reactor, there we can create the pressure on the floating ball so that the injection of the poison into the calandria will be very smooth, and it will also ensure the integrity of the entire process. And so coming to the point, when it's when we need to pressurize the floating ball, definitely we should pressurize the floating ball when, I repeat, we should pressurize the floating ball when any of the trip parameter of the reactors comes. Trip parameters, like I said, in the case of human being, for example, kidney failure is a trip parameter. Trip parameter means those parameters on which I have to trip my reactor, or I have to shut down my reactor. So you can look back, again to the originating point from where it is connected. So you can see this floating, this poison tank was connected with the several set of valves where the kick opening valves are written. And we will see what is the significance of so many valves. And but you can see, like, if you more backtrack from this kick opening valves, it is connecting to the helium supply tank. And why helium supply tank? Because it can easily create the pressure. So just think in place of these valves, there is only one valve, like tap. When in the washroom, when I want to wash my hands, I open the tap, and otherwise I close the tap. That's it. So what I can do, like, I can keep here one valve, and when there is a trip parameter, I can open this valve so that the helium gas can pressurize. The pressure of the from the helium gas will be transferred to this floating ball, and which can pressurize the floating ball to inject the poison tank into the calandria. And and why we have taken the helium? Because it is an inert gas also, so it will ensure the integrity of the entire process. It will not undergo any chemical reaction which can jeopardize the integrity of the process. Now coming to these valves, why are so many valves? If I said one valve was enough, when I want, I can open that valve, or when I am done, I can close the valve. But why so many in this case? Let's try to understand this. Suppose there could be only one valve, then suppose the trip parameter comes and we have to open that valve, and we could open that valve and the helium could have reached, pressure could have reached to the floating valve. But what could be the problem if there is some mechanical failure a mechanical malfunction in the valve which restrict the opening of the valve on demand, and valve got stuck to open. This is one of the failure mode of the valve that can happen. Then we will not be able to inject the poison in the calandria when it is really in the demand. So what we have to do? How we can, take the remedial action? Why don't we put one valve in the parallel so that if one valve is not able to open on demand, at least the other can open and we'll be able to shut down the reactor. That is fine now. Okay, I can easily, I'm convinced that two valves are sufficient. Then what is the problem, like why we have taken rest of the valves? Now consider I have injected the poison, and after maintenance activity, or I want to restart my reactor, then definitely I'll have to close this valve because now I don't want poison to get injected into the calandria. So when suppose the way we considered one failure mode that it got stuck to open, we can also consider another failure mode it got stuck to close. When I really want to restart my reactor, and when it will stuck to close, it means then I cannot stop the pressure from the helium. So what happened? Let us put one more valve in parallel in each line, sorry, in series, in each line or in each parallel. So what happened? This valve, if suppose one was stuck to close, the other one will be able to close, it will get closed, and we can ensure now it will not pressurize the poison into the calandria. And in this way, to handle the failure mode is stuck to close, I have put two more valves, one in each line. Now, what is the problem then? Okay, now I have considered all failure modes of the valve. One is stuck to open, one is stuck to close. Now, why we need these vertical valves then? Let's try to understand. Now, suppose in case of normal condition, I mean normal in the sense when my reactor is in power mode. And so what happens, like all these four valves will be closed because I don't want any poison to get injected into the calandria. And then what happens? Suppose there is a malfunction in this valve which is leaking basically, and the pressure is also leaking in this line, horizontal line. So what it can do? It can also malfunction the second valve, and probably there could be a time where the helium starts leaking from the second valve also, and which can pressurize the floating valve and has a potential to shut down the reactor. And hence, just to vent the pressure that can build in this line, we just put one vent valve so that and let us keep it normally open. So there will not be possibility that the pressure is building up in that line, and all the pressure will be released to the atmosphere. And similarly we have to do with the second line also. So now how the working will be taking place. Generally, all these four valves will be in closed state, and these two vent valves will be in open state. And when there is a demand to shut down the reactor, first we'll have to close the vent valves and then open these quick opening valves or fast acting valve. Why? If we would not first close the vent valves, all the pressure would have gone out to the atmosphere after opening the quick opening valves, and we would have lost the helium, which is economical loss, and the safety loss is we will not be able to shut down the reactor, and the radiation can be exposed to the public, and you can understand the consequences of the radiation considering the accident that was happened in the Hiroshima and Nagasaki. Still, the effect is persisting, because we know like radioactive elements have a half-life that ranges from milliseconds to billion of years. Okay. And once I'm done with injection and suppose all the maintenance activities have been done, I'll have to reverse the logic. I have to first, open the vent valves and then, close all the quick opening valves. In conclusion, after understanding the working mechanism of this system, we could conclude that other than these valves, all are static in nature. All the mechanical equipments are static in nature. They don't have any dynamics. And these valves are basically dynamic in nature. And once anything is dynamic in nature, it is more prone to fail, to undergo failure. So we in the modeling only we have to look with respect to these dynamics. So now let us try to model this operation of the valve. So here, this figure, it is basically the Patrinet model of that particular system, and where we can see like the places and the transitions which are interconnecting, and interestingly, all the weight of all the arc is 1. So I have not kept any weight. So when we don't keep any weight, by default it is treated as 1. So let us first understand the working mechanism of this model that we have created. So there is a PPD place where I have shown the token. It shows like any trip parameter has been deviated and there is a demand to shut down the reactor. So when there is a demand, there is a trigger TTPD, which basically on firing, which fires send the signal to create any logic condition and to energize the relay to close the vent valves. Because the first thing is we have to close the vent valves. So we have to energize the electronic relay to close the vent valves. And then we have to create the logic condition. So PLC on is creation of the logic condition. Now what is the logic condition? Logic condition means now the trip parameter has been taken place and what all the set of valves needs to be operated in which sequence, as well as it is a flag which is basically which is a symbol that now the trip parameter has been deviated and the process is going on. It is like when I'm passing to the road and somewhere the construction work is going on, and where it is showing the flag that construction work is going on, and hence I have to take the alternative path. So it is just a flag, and then we'll have to hold that flag. So TLCH is the transition, which basically triggers the signal to hold the logic condition in the created state. And then PLCH is the place which represents the logic condition is on hold condition. Now, from the in the vertically or in parallelly, you can see from the TTPD, we have to first, energize the relay to close the vent valve. So PREVV is if there is some token in the PREVV place, it will energize the relay to close the vent valve. Then it will go to the TVVC, which is the trigger to close the vent valves, and then it is coming to TVVC, which is basically the which shows that vent valve are closed now. And when the vent valves are closed, we have to open the fast acting valves or the quick opening valves. So this is the trigger TFAVO, which basically opens the fast acting valve. And when it sees that already the fast acting valve is in closed state, I have already shown by putting a token, and then it can pull out the token and it can lead to the fast acting valve in the open state, which is shown by the place PFABO when the token will be on this place. So it will now, inject the poison, and now there is a demand. Once I have done all the maintenance activity, I have to restart the reactor. And so once I have done the activity, I have first put my logic condition in off position. So this is TLC off will fire, and after putting off, which can be shown by the token in PLC off, PRDPB, which basically shows that relay has been de-energized to open the vent valves, because the first thing when to restart or reset the system, we have to open the vent valves, and then it will trigger to open the vent valves, TVBO, and here the TVBO means vent valve have been opened. And after that, we have to close the fast acting valve or the quick opening valve. So it will trigger to TFABC, and it will close the fast acting valve, where I can put the token in the TFABC. This is the entire, I have captured the dynamics of these valves in the model. Only but two interesting places I have not touched. Let us talk about this. One is PFABCD. It is PFABC only, but it represents the redundant information because it is an important activity or important state. So for that, redundant sensors have been installed, which basically tells the state of the that particular component. Similarly, the redundant state of the fast acting valve open also we have kept. So this is the entire modeling. Now coming to the safety analysis part. So how we have to do that. So now the whole idea is we have to find out what would be the number of states that are possible throughout the operational time of this system. So how we can find out the state, as when we saw the working mechanism of the battery nets, we could see the reachability analysis or the reachability graph was helping us out to find the states of the system. So let us draw the reachability graph, for which we have to start with the initial state, that is S1, and it should contain all the places which contains the tokens. So the tokens are in PPD, PFABCD, PFABC, because these places will only be responsible to change the state, and rest of the places does not have any token, so they are not responsible. So just you can write it down, only these places. So I have written S1 is PPD with PFABCD with PFABC. Then after that, let us go back and see. This transition is fired, TPPD, and the token will move out from PPD to PLC on and PRE, and rest of the distribution will remain the same. So here what I have done, just I have replaced the PPD, and after firing PTPD transition, the token distribution now has been moved from PPD to these two places, which is PLC on and PREBB, and rest of the places are same. And similarly, we can keep on building the reachability graph till we identify all the states, and this is the reachability graph. So basically, it is showing all the possible number of states, and now we have to analyze the risky states. So if you are able to see in this figure, S3 and S6 are the risky states which are marked by a solid triangle on the left upper portion. And why this is a risky state, let us try to analyze. So we can see in the S3 it is written PLCH, means logic condition is on hold. And then PREBB and PFABCD, it means my fast acting wall or the quick opening wall is in close. So this is a very risky state. I have created a logic condition, means there is a demand to shut down the reactor, and then also my quick opening walls are in close state. So this is a risky state, and hence I don't want this state to be confronted. Now, coming to the S6, you can see once it is written FABO, it means the fast acting valve is in open state, and it is written FABC, means it is in closed state. So it is a controversial state. It is a conflict state, and I need to avoid because I cannot rely on anyone. So these two states, if I find these are the risky states. So first thing is we have identified what all the risky states, and now we have to tell out, or we have to formulate a way out where we can avoid these risky states or avoid these states basically. So how we can do that? If you backtrack, first let us consider the S3. From S3, just try to backtrack from which it is originating. So it is originating from S2. And from S2, you can see there are the two states that are originating. One is S3 and one is S4. And S4 is a safe state. And these two states are, coming from firing of two transitions which are in parallel, that is TLCH and TVBC. And because these are parallel, so it means these transitions are in race condition. So definitely one is reaching to the unsafe state. So we have to prioritize one transition, that is PVBC. So one thing is very clear. Whenever these two transitions are in race condition, I have to always prioritize TVBC so that I can ensure that TLCH will never fire and it will not lead to the S3. Now coming to S6, when I backtrack, we can see it is initiating from S3 as well as S4. And now there is no possibility of S3. We have already, identified the remedial action that S3 will never be confronted. So coming to only S4, we can see again from S4, there are the two states that are confronting. One is S6 and one is S7. So whenever these two transitions are in race condition, just prioritize one transition which is leading to the safe state. That is, we have to prioritize the TFABO. So one thing is very clear what needs to be done. We have to just prioritize the transition which is leading to the safe state. And how then it needs to be done in the modeling. First we'll have to do into the modeling, and then we will come with the implementation part. So coming to the model, it is very simple. Just to introduce two additional, places, and I want to always, put the TLCH on the lower priority. So the transition which I want to put on the higher priority, just from that, connect to the lower priority transition by putting the place in between, so that every time, whenever the TVBC will fire, then only the token will come in that additional place, and which is the input place of the lower priority transition. So it will not. So whenever these two transitions will be in firing state, only TVBC will be given the high priority. Similarly, I want to prioritize the TFABO with the TLCH. So again, I have to put one additional place, I2, and sorry, I think I1 and I2, these both are looking I1 and 2 are missing, I think. So and the same thing will valid here also. And now after modifying my Patrinet, just to address the safety issue, I can again redraw my reachability graph, and we can see after redrawing, considering the I1 and I2, I'm not able to find any risky state. But the story doesn't end here. We have to, these additional places are not going to perform any role for fulfilling the functional requirements. These are only for fulfilling the safety requirements. And hence, we'll try out to find some way if we can at least, minimize the number of additional places, because addition of the number of places will increase the number of states also, and which can, increase the complexity of the system. So increase the computational complexity or the space complexity. And hence what we can do, like we can first we can consider two cases. In the first cases, only consider I1 and ignore I2, and then draw reachability graph. In the second case, consider only I2, ignore I1, and draw reachability graph. And then see whether any state is in risky state. So here, this is an example where this is a case where we have considered only I1, and again we found there is one risky state which is marked. And when I had considered only I2 1-2 state, then this is the reachability graph that I got. So it doesn't contain any risky states. All the states which are marked by the solid circle, those are the end states, are not the risky states, basically. And now let us come to the implementation part, how it should be implemented. So we know, like real-time operating system, it provides a feature to the application software which can help prioritize the tasks. So the other way to impose the precedence among the parallel transition to avoid the risk state, we can, to enforce the firing of transitions as per the defined priority. And so how it can be done? It can be done by enforcing, timing constraints in the design. So in the case of our study, we have to keep this constraint, that is minimum TLCS should always be greater than maximum of TFABO. So we can ensure that always TFEO will be given the highest priority, because we have, the time delay is less, always be less for this. And this constraint must be checked by hardware or software logic as per the requirements. And if the system fails to meet this constraint, the logic must be built into the design so that the control reaches back to the originating state of the risk state. And so that, it can retry the processing meeting the same previous constraint, same states. And this logic can be achieved by the soft watchdog or the hard watchdog. In case of the hard watchdog or module, hardware logic must send a periodic pulse to the watchdog. And the moment the constraint given in that equation which we have shown fails, it must stop sending pulse to the watchdog, and the watchdog must maintain the current and its previous state. So once watchdog stops getting periodic pulse, it loads all the dynamic variables which are of previous states. And the other possibility is to reset the microprocessor IC through reset pin, and which will reset the system state. And this watchdog can be implemented as the software watchdog, known as soft watchdog. Or hardwired, then it will be known as hard watchdog. So in the case of software, then software has to send the periodic pulse to the watchdog to process in the same manner as hardware does. Now we have touched upon the implementation part, but once we deal with the engineering, we always strive to the optimum solution, and hence we'll have to look, possible worst scenarios to make my system robust. For example, in our case, I have created a logic condition to trip the reactor, and the embedded system closes the vent valves, but there is some bad signal comes which overrides this closing logic. Closing logic of quick opening valves when the reactor shutdown was in demand, and which can be identified by the inconsistent information in the PFAVO and its redundant place, and PFAVC and its redundant place. So it could be a real condition or it could be a fault, but a logic must be built into the design that in either case, always the system will treat that quick acting valve or the fast acting valve in the closed state and resend the signal to open it immediately. And how it can be done into the modeling? First we'll have to, because everything first we'll have to embed into the design. Once we are able to embed into the design, it can easily be, handled. implemented. So this can be done by introducing a new safe transition, TSFAB. It is a safe transition, FAB, so that, whenever such condition occurs or not occurs, it will always see the trip parameters is there, and it will pull out the token from the fast acting valve closed state, and intentionally it will put into the fast acting valve open state, so that all the time it can ensure that the quick opening valves will be opened in the case of emergency. And now, so again, we can see the firing that if there is some conflict into the states, we can prioritize the states in the similar fashion. And this design can again be validated by drawing the reachability graph. So you can draw the reachability graph, which we can see. Now all the states are risk-free states. And in this way, we can, more and more we can investigate the process with respect to the domain knowledge. So it may be a time-taking process, much effort may be required, but the benefits outweigh them, looking from the safety perspectives. So in conclusions, we can see like the analysis, safety analysis can be decomposed into various segments. Suppose, for example, you are dealing with a large system, or your system is very complex, then you should understand, with the help of the system analyst, you should identify the criticality of the various functions, and you have to put into the hierarchy, so that, because you should know, like, all the risks do not have equal probabilities. So the functions which are more responsible to perform the most critical functionalities of the system, just identify those functions, and you give the priorities or more rigorous analysis to such kind of systems. And you have to develop the modules also in the hierarchical fashion, so that, the critical functionality you have to keep in one module and the non-critical into the other module. Because, always the non-critical function should not give any command to the critical function, while vice versa only should be there. So, and then you can perform the analysis in parts, probably by component or function by function, in case, the volume or the criticality of the function is very much. And in the similar fashion, the analysis, can be done for rest of the component connectors as well. The interfaces are very important, because interfaces is used to pass the message from one component to another component, and it should have a proper validation mechanism, that which thing needs to be filtered out and which things needs to be propagated to the next component. So in this way, like, definitely we can do that analysis. So we have seen, like, PatriNet is a important mathematical formalism, where not only we can analyze the safety, but also other non-functional requirements or the dependability attributes, for example, reliability, performability, security. Those can also be modeled out, because it has a good capability to capture the dynamics of the system. And the traditional models basically, assumes the stochastic independence, between the component failures. But here, stochastic dependency in the sense one component may fail by itself, but it may also be failed by other components, other adjacent components. That also, that kind of flow or that kind of aspects can also be modeled using this Patrinet. So that's all I wanted to conclude. These are some of the bibliographies if you can use. And in case of any questions, I'll be happy to answer those questions.
So please look into the chat box if any questions are there. I find one that is how to decide token value in firing. And privately also participants, they may write in chat. Please check.
Yeah, they can write in chat, or if they want to interact lively, they can also interact lively. So coming to the question, how to decide the token value in firing. First of all, the question, I'm not able to understand the meaning of that question. Token value in firing. What does it mean? Can you please? I think Amrita Deshpande have written, right? So Amrita, can you please unmute and can you please explain me so that I can answer your question?
Yeah, please unmute Amrita.
Hello,
Yeah,
Yeah, please.
am I audible, sir?
yeah, you are audible. Please tell me.
Sir, you have shown the example of H2O and some tokens also you have shown. So
Right.
likewise, the two tokens are there for hydrogen, two tokens are there for oxygen,
Right.
and for two types of H2O, actually no tokens were there.
Mhm.
So,
Right.
I mean, while firing, how will you decide how many? I mean, whenever we are trying to shift down, how will you understand? I mean, decide how much tokens will be there?
See how much tokens at the initial state. For example, it depends on your context. For example, here I was representing the token to represent the number of atoms, and it totally depends on your system context. What you want to represent the token is. Ultimately, the crux is you need to understand the tokens are basically responsible guys which can change the state of the system. So you have to analyze your system with respect to what are the attributes that are responsible to change the system. For example, if you can see the case study where the token was used as a trip parameter and some of the tokens were used to represent the state of that particular quick opening valves or the other valves also. So basically you have to define the tokens with respect to the context, and in case if you are dealing with a complex systems, there is a concept of a colored patronage where you can use the colored tokens basically to represent or to memorize like what particular color of that particular token is representing what dynamics basically. So it totally depends on that, and the firing rules basically depends on the weight of the arc. So accordingly, we'll have to keep the weight of the arc. So it requires the system expertise, the system domain, in what way you want to, the basic idea is you need to understand the behavior of that system. What should be the behavior of that system during the runtime, and that behavior you should represent in the modeling aspect. So you should understand the behavior and how you are going to represent the behavior in the patronage that you have to develop the model accordingly.
Okay, any other questions are there? because in chat box I don't find any questions. But if somebody want to ask directly, they can raise their hand.
I have specifically kept a marginal time for this questionnaire session, so the people are free to ask. So.
Please, you raise the hand so that we can unmute. So raise the hand option you will find at the bottom.
Okay, I think nobody has the question. They are always free to connect me in case they do have a questions offline also. So I don't mind responding them.
Okay, I will share your email ID so that even if they have any questions for their studies, they can communicate here as well. So thank you very much, Dr. Lalit Kumar Singh, for associating with us and delivering a lecture on this safety analysis of mechatronic systems. So fortunately, we come across and actually by face today only we look to each other. But nicely with only email communication, you have accepted our invitation and you have delivered a wonderful lecture, which is something different than a very academics. So the students might have benefited the actual implementation of these techniques. Thank you very much for that.
Thank you. Thank you. Thank you.
Yeah, for participants now, some couple of instructions are there. The instructions are, actually it is posted on the group also. So at 3 o'clock, we will display the link in this chat box as well as in WhatsApp group. So 3 to 5, you have to, first of all, you have to log in. So don't log out. Okay. So at 3 o'clock, you please log in and simultaneously you see that link as well as you be log in and solve the, MCQs, you have to solve it and then submit either 5 o'clock or before 5 o'clock. Okay. This is one announcement. The 100 marks quiz is there. And it is multiple choice questions. And you know, as per AICTE guidelines, you should score either 60% or more. Then only you will be eligible to get the certificate. This is one condition. Second condition is attendance 80% and more. Then once you submit, then 5 to 5:15, around 15, within 15 minutes or so, we'll finish our valedictory. So I request all of you to be present there. And a few of the students, participants, they have expressed to speak in the valedictory. And those who want to speak, definitely they can contact either on this group or separately to us, to the panelist. Okay. And within that feedback, we will circulate the last link, that is feedback link, a overall feedback about this FDP. Okay, so it is an overall feedback that is how the FDP is, how the experts were, and even you can write whatever things you want to write for either improvement or for the compliments also. So that all we will share after you submit your quiz. Then we will give the feedback, and that feedback you have to fill up. One more thing you should not forget, on the ATAL portal, through your login credentials, you have to fill up the feedback. Okay, now the feedback link, it is open in ATAL web portal. Without that feedback in ATAL portal, that is, you have to fill it, and without filling, you won't get certificate also. I think that might have some arrangement, they might have did it. Okay, so after this course, maybe today evening or tomorrow, you please please fill up the feedback on the ATAL portal also. So these are the instructions. Now you can take rest or you can read, and by 3 o'clock we will circulate the link. Thank you very much. If you have any queries, you please write in chat box. I am sitting.